say at all about the second law of thermodynamics.
Same.
They know
It's
nothing
Just because of
about
that one question,
there's
you're being
a
an idiot.
conspiracy, bro.
Okay, how about what question?
I mean, wake up.
What question?
Of entropy.
It is a very basic question.
Is there
No, he gave us the answer.
Okay,
Danny,
give
Danny, let
them
me finish
one
this.
of three. One of three.
Danny, there's two parts to it. There's reversible and non-reversible, just to let you know where I'm going with this. So I need to have the floor. Just ask the question.
Exactly.
Don't be rude, everybody. Just if you don't know it, you don't know it. But if someone knows it, please let me know. Arwen, anybody?
Is it not? It stays the same. It doesn't change.
No, it actually goes up.
Pardon me. The total entropy.
The total entropy of that system goes up. And the reason why...
What is the entropy? What tool is used to measure the entropy? What tool do they use? And
you can use several
gauges and
measures.
what units is it measured in?
Easiest way, well, if you can use Boltzmann entropy, or you can use Clausian, but you can measure pressure changes and temperatures, and you can measure entropy that way. But don't get into the minutia of this test. Just stay high level. This is what quantum racer always talks about.
Wouldn't the total stay the same, though?
No, it doesn't. And he talks about this. He says, the membrane breaks, the high pressure moves to low pressure, the temperature stays the same. But what does the pressure do?
The total pressure stays the same.
No.
Yes.
Think about it. I have 1,000 psi in one chamber and 0 psi in
okay,
two
so it goes in half, right? Yeah.
Right. Yeah. That's your indicator. So what happened to this? The temperature didn't change. The energy wasn't added or subtracted to the system. So what does the entropy did if that pressure actually went down by half and the temperature stayed the same? Let me give you a hint. Can that pressure do any more or less work now that it's expanded into two chambers?
Less.
Yeah. So the entropy had to go up. Okay? But that's a very unique system. That's free, call it free expansion. That's what he refers to as our atmosphere and why it doesn't expand into the universe. Now, the second part of this question, an example, is that if you have now a piston that has made that same chamber 1,000 psi, but there's weights on it, keeping it in position, and you start removing the weights, and the piston moves up into that same size volume as the first example, and I get the same exact volume now, where the pressure is that same exact half the pressure. What did the temperature do in that situation?
Increased.
No.
What? What happened?
No.
What's your example?
The first example, it didn't change. We all agree, right?
The second example.
The second example, the piston goes up and makes the volume larger till it stops at the same exact volume as the first example.
You're saying the temperature would decrease?
Why would it decrease? I'm not saying you're right or wrong.
No, you're right. It would
no, I'm not saying you're right or wrong. I'm just saying you might be on the right track. Why would it decrease?
Well, I was thinking the other way around, where your pistons close.
Well, no, think about it the way you are, because you're a mechanical guy. Think about.
Well, that's why I said increase, because I was thinking about the piston closing in to create pressure back.
No, yeah, it's not. It's the other way. So maybe I didn't describe it right. You have a high pressure, 1,000 psi, like a piston in a cylinder, and the piston goes down due to that pressure, and you're letting the emergency brake out of the rear wheels that are connected to the transmission, and you're letting this thing.
Mic check. Did I lose you guys?
Yeah, Discord went out. Xanet, before you start over, can you name that entropy level again? What did you call that state of entropy?
Check.
Xanek, are you there? What did he call that entropy? Do y'all know?
It's just whatever value it is when it started.
No, he gave it a name.
He gave it a name.
Yeah,
that was for measuring it. Right?
He called it something. Okay, never mind.
You're talking about the two different types of measurements he was talking about? Is that what
no, he gave that type of entropy a name. It was a special case. He called it a special case, and then he gave it a name. What was the name of it?
Something like open flow or something.
Free expansion?
That's
free expansion. Okay, thanks.
Are you back there, Grant?
Can you guys hear me now? Sorry about that. My computer took it.
Hey, Xanet, before you get going again, was that free expansion you called that?
The
State of
first one was free expansion. The
Yeah.
second example was it pushing a piston down and moving the car, but to eventually get to the exact same volume as the first example, which was free expansion. So what does the temperature do in the second example when it pushed down the piston and moved the car? Now we ended up with the same volume as the first example, but in this case, it wasn't free, right? It actually moved the car. So what does the
You're
temperature
stretching
do?
the material inside.
What?
Wouldn't the temperature go up then on that?
You're stretching the material inside.
No. One more time real quick. I'm sorry if I'm explaining it wrong. Look, the first example had a membrane, and we broke the membrane and the gas free expanded, right?
Oh,
We talked about that for a second. Done. Second example, we have a piston that is compressing that air. It's compressed. Same PSI, 1,000 PSI. And we have, let's say we have a weight on, and it's going to go up. So we have weights on it. And we start removing the weights, and the piston starts going up as that pressure starts pushing against the piston, and eventually ends up at the same volume as that first example.
And you start with the same pressure.
So the pressure
you started
isn't
with the
pushing
same
the
pressure.
piston.
The pressure is pushing the weights up, and we keep on removing more and more weights, and it keeps on going higher and higher until it ends up to the point where it has the exact same volume as the free expansion 2 chambers. But now we've got there through a different path. But we ended up with the same volume and the same pressure, which is half of the original 1,000 psi. It's at 500.
And how
So
fast
what did the
was this
temperature do
process?
now?
How
What?
fast was this process?
Well, we're isolated, so it doesn't really matter.
Shouldn't it stay the same?
No, it did work.
There was work done, so there was energy, there was heat loss.
Perfect. Yes. So the two difference between the two scenarios. One is free expansion, temperature doesn't change, pressure went down. Second example, pressure went down, same way, but temperature went down where it didn't before, and the pressure went down by half, just like the first example.
Wait a second.
The difference
On
is
your
the work.
second,
The work,
on.
yes, exactly. That is this is entropy in its most raw form.
You
Hold on a
said
second.
you misspoke one thing, Zanik. You said that the energy was lost. It's not lost. It's just
Yeah, it's not.
distributed differently.
You were talking about the heat. You said energy earlier.
Yeah, but hold on.
Work was done.
But how do you explain work was done? Because the way I'm kind of seeing your example, and correct me how I'm not seeing it right, but basically you're having a force. Yeah, but basically you're having a force stopping that piston from moving. It's overcoming the 1,000 pound pressure that you started with.
Right.
But as you move the weight, it's not really working because you're just moving the force that's holding container at the size that it is.
It has weight, and it takes a force, and it takes work and energy to actually move a mass, and that's what we're doing. We're lifting this mass some distance to get that volume, what we're talking about, and that work done, force over a distance, is that is the work, force times distance. So by doing work and using energy to do work, that energy now is still in the system. It's just now in a form that is not usable anymore. So the pressure went down and the temperature went down. Where the first example, the temperature didn't go down.
This is called, okay,
So
this
the
is
point
referred to, oh, go ahead.
It's referred to as a reversible process because we can
Yes.
easily put the weights back on that piston and push it back down and recompress that air, can we not?
Yeah, jumping again, you said where the pressure
And the
goes
temperature
down,
go back up,
goes down.
and the pressure go back up, and everything's the way it started. It's called reversible. So the difference is in one scenario, entropy went up. That's what quantum racer likes to use. The second example, entropy doesn't change at all. No change. However, think about it. Gas expanded. It went into a larger chamber and spread out. Why does entropy not change? See, that blows a hole in saying that entropy is
The volume increased though, right?
in both situations. Volume increased. Yes.
Yeah, but there was work being done in one. That's the difference
Correct.
in the entropy.
Yes. So does air have weight?
Of course it has weight.
Does air have weight?
Yes.
So if air was going to escape into space, wouldn't that weight require a force or work to be done for it to move it?
Yeah, but you're equating it to the
Can
atmosphere.
there be free expansion? Oh, let me say in other words. Can you have free expansion if air has weight? Can you? If air has weight, can you have air expand freely? And it's not a trick
Yes.
question. It's very clear.
Yes.
Really? Air has weight, you have free expansion.
Yeah.
Sorry, wrong answer.
It has to do work.
What's the weight of the particle that's accelerating away from the Earth? What's its weight?
It would have to do work.
Still has weight.
In other
its
words,
weight?
for it to expand, it would have to do work.
That's right.
So the gas particle that's expanding out is not doing work.
No, it is in the atmosphere.
There it
Those
is.
this goes up to work.
What's the weight of the particle that's accelerating away from the Earth? What's its
It's mass,
If
it's mass
if
times
it's
the
an
acceleration
oxygen
of gravity.
molecule, then it's O2. So whatever the molecular weight of O2 is.
He's talking about
28 grams. 28 grams for O2.
No, but that's why I said you couldn't equate it to the atmosphere, because as soon as the gas is going up, it's doing work. The collisions are work. Everything is work.
No, the collisions are not work.
No, collisions
Those
are not
those
work. It's just a
elastic
transfer.
collisions. Those are
It's
elastic
not work.
collisions. There's no work being done on the collisions.
So the elastic collisions on the piston does not work.
No, it is when it causes it to expand. When you move the piston, then it's doing work.
When the
But not
piston
just when-
moves, the air slows down, as it stated.
Takes
Like
kinetic
Doppler
energy,
effect.
transfers energy. There's a conservation of energy here. What happens? The molecules hit the piston. It starts to move. It takes energy away from those molecules. The temperature goes down. It's a very simple. Temperature is the speed of the molecules. Do we all agree? See, this is simple stuff, guys. If you just
Wait,
use
don't
the
say
molecule-
that. You ain't got to go there. You ain't got to go there.
Well, I'm
it's
just
not.
saying
It's not
it's
that
clear.
simple.
Well, no, it's not simple, but we're making it simple for you, so you understand it. So you realize that entropy is a lousy argument, and it's misunderstood by everyone in that chat.
No, you're just to simplify then, to make it simple.
I'm making
you're just
it
saying
simple.
basically.
The entropy-
Okay, let me. Jesus,
Wait, let him ask.
Xanax,
He's gonna
Xanax.
ask.
Holy crap! So basically, you're just saying the natural laws allow gas to settle down.
Is that what you would say, Zanuck?
I don't think
No,
so.
The
I don't even- I know what
combination
that even
allows. Why no?
I don't know what that
Gases never settle.
means. They don't?
So
Well, I
the
mean,
weight,
The
way
heavier
that it
ones will
is-
go lower than lighter ones, but they never settle.
Well,
Yeah, I
they
don't know
will
what that-
freeze
I don't know-
eventually.
I didn't know what he's trying to say, so if he could rephrase it, it might be better for all of us.
The
Yeah, go ahead
only,
and
the
ask
only,
it
the
again if
only
you want.
reason they don't settle is because we have a sun that heats them up.
That's what we're talking about, the atmosphere, right? That's what we're equating.
Oh, you're talking about.
That's-
Okay, so in other words, this is a good question. Does gravitational clustering cause an increase or a decrease in entropy?
Right.
It would have to
That's
cause an
relevant.
increase, right? Because it occurs. Does that make sense to you?
Yeah, but there's no, like we said, there's not like there's any measuring machine. It's a perspective
Perspective.
I'm sorry.
based on all your other measurements. All your other measurements of pressure and temperature and all that, those are the real measurements. And then you have a
We measure a
perspective.
gradient. We understand gas law. See, you can't use ideal gases and Boole's law and talk about containers when we're not talking about the atmosphere being ideal gas. So why would you even want to use an ideal gas law? Why would you use free expansion when when it's not free expansion? All these things add up to like a bad argument. I mean, it doesn't take a master in physics to figure this one out. It's just using normal everyday
See,
logic.
I don't think they do. I understand that the gas, like I tried to summarize, gas can settle, but and I do know that it's obnoxiously positioned, as personally I feel from the fire, but like it still gets you to the position where we're like, okay, the air is clung to the earth in a kind of a special conditioning. Please prove it. You know what I mean? Like instead
Well-
of arguing how possible it is, let's just prove it.
Well, for one, I think if I'm not really sure what the argument is from the flat Earth side because there's so many different forms of it, but it seems to hinge on the claim, on every small scale experiment that you can do on Earth in a laboratory, gas that's confined in one container will expand into the other container when they're connected without a physical barrier between them, right? That's usually what it's based on. It's based on, every single time you're in a lab, if you had whatever, any container with gas in it, and then you connect it to another container that's at a lower pressure, that is going to expand into it. But that's a small scale demonstration. So then the question would be, and this is more of a like what you're doing is you're begging the question when you make your conclusion that, well, therefore the atmosphere must be contained inside of a container, because how does small scale demonstrations of you're on a small scale, on a laboratory scale, how does that allow you to make a conclusion about the entire atmosphere?
Yo, look, I personally agree because I can even see gas settle down on a small scale, but I mean,
Well, Danny,
I don't like
to some degree, you
But like
guys
I
do
said,
this. Oh, sorry, dude.
just like I said, yeah. I mean, so
Make
we're
sure you look
saying
at his hand
it's
before he comes
possible on
back.
a large scale. So can we just
Yeah.
prove the large scale? Can we just?
To some degree,
Look
you
at it.
guys do a similar thing, Danny, by saying we see a gradient go so far, therefore it must eventually go to zero to a vacuum.
Well, not necessarily the case, but we do see a gradient, and that is not the same behavior that you see on the small scale. So for the example of, a container on a laboratory bench where you connect it to another container and you have a physical barrier, then you remove it, and then the high pressure goes to the low pressure, it equalizes, blah, blah, blah. That happens on a small scale. You don't see a gradient form on that small scale. So we know that there's something different going on in the atmosphere just by the sheer fact that there is a gradient, which is why it's constantly brought up.
Okay, so
here's the
what
problem,
about?
Danny.
Hold on a sec. What about like a gas well? You can measure a gradient within a gas well. Like in Canada, I've worked on wells that are up to 3,000 meters deep. That's 3 kilometers. I don't know what that is in miles, but it's quite deep. And we can measure a gradient in there, and these wells still operate on this idea that if the well's on a vacuum, it's going to suck when you open up the valve. If it has pressure, you open up the valve, gas or air, whatever's there is going to escape.
Yeah.
That's a large
That's
scale.
Yeah, that's a larger scale, but within the gas, that's even in that large scale, you're saying that there's a gradient inside of that well?
Yeah, they do these things. You can look into it yourself, anybody that wants to. It's called
Well,
wire lining or E-line, electric line. It goes by a couple of different names, but they have tools that they put down there, and they actually
right.
measure gradient, pressure
So let's
gradient.
say you have a giant 50-meter well, okay, and you go to the bottom of the well, and then you go to the top of the well, and it's closed, and you say, okay, I see a gradient in here. It's a closed system, and it's a gradient. Then the question might be, is it a necessary condition that there is a container for there to be a gradient? And the fact of the matter is, if you look at, like, say, the second law of thermodynamics, right? There's an equation called the Maxwell. It's an equation by Ludwig Boltzmann, who is credited. It's even written on his tombstone. He has the equation that he discovered written on his tombstone. It's an expression for entropy. He also derived an expression that is a law called the barometric law that describes the pressure gradient as a function of altitude. And he derives that law simply based on entropy, just considerations of entropy, and the ideal gas law. And when you watch him do it, if you go through the derivation, you realize that a container is not required. And in fact, all that is required is that there's an acceleration field. And in this case, it's the gravitational field.
Well, I mean, to make a Nathan Oakley argument, I could potentially make the argument to say, well, maybe you don't need a container to find gradient, but you do need one to have pressure.
Well, why would you need one to have pressure? So he jumped all over
Because
Danny Faulkner about. Hold on, Danny Faulkner criticized flat earthers as saying they misunderstand gas pressure as needing a container because they think the pressure is all happening at the edge of the container. And Danny Faulkner actually was incorrect and wrong as to assume that, because Quantum Racer got excited about that comment he made. What he said was, we need the container to make the pressure not only at the edges but through this container. So that's what they say. But as Danny's mentioned many times, his atmosphere law talks about there a pressure gradient due to this hydrostatic pressure where the cause is.
Sure, but I know that maybe Quantum Eraser and Nathan Oakley don't necessarily agree with this idea of hydrostatic pressure, but it's an idea that I have mentioned months ago myself and have considered. And if I give hydrostatic pressure, I know right away I'm saying, well, in the formula it has little g, so there you go, blah, blah, blah. But that aside, if we go with the idea of hydrostatic pressure, you still technically you need a container. It doesn't have to have a top on it per se, but you need something like a glass to have hydrostatic pressure.
We have to have
What's wrong with gas? What's wrong with gas? Why does it have to be glass?
Well,
Well,
wait
no,
a second.
no. I was just saying. I just used the
be
glass
clear.
as an example to have a container, but
well, you need a
to
surface
have
for it to act
hydrostatic
on.
pressure.
You do need to. So yes, we have the container is the surface of Earth. That's the container, a surface. All you need is a surface, and then there's molecules acting on that surface.
It's not, and to be clear, to be clear, it's not a necessary condition. So if you're, the only claim that I could see a flat earther saying, coming to this is say, well, it still doesn't rule out that there's not a container, and that's it. Because you can't, because what it does say is that it's not necessary that there is a container. So if your argument is going to be, oh, well, we know that there must be a container because it's a necessary condition for there to be a gas pressure, well, then you're going to have to cite that because there is nowhere in any scientific literature whatsoever that says that it's a requirement, that is a necessary condition for there to be a physical solid container for there to be a gas pressure.
Well, just to be clear, that's claim exactly that it has to be. But I would say every experience we have on the Earth, except for, in quotation marks, apparently the atmosphere, we do have a container. Like, even if you want to take it out into the ocean and say hydrostatic pressure every 33 feet of seawater is equal to 1 atmosphere, and that's due to hydrostatic pressure, blah, blah, blah.
That's due to the weight of the,
but
that's due to only considering the weight of the water.
You're still in a container. The water's contained. Yeah, go ahead.
There's something. There's a false equivalency going on, and nobody's caught it. Danny just said a gravity field. Okay. Now you've also said that the weight. So are you equating this gravity field with a weight field? Is that what you're saying?
Well, yes, that is what is giving particles weight.
So it's a weight field. So it's the weight, not the gravity. So which gravity is it again?
Okay, so the which gravity thing, it doesn't even necessarily change anything.
Yeah, we're not arguing about the shape of the Earth because it could be flat.
That's okay.
Container, flat, no container. Round and container, round and
It's simply, Paul, I've explained this. Paul, we can go down this line of dialogue, even though that it's gone down. We can go down this little line of dialogue, and I already know where it's going to go. But do you know what I've said to you before about, and I'll give you a hint, about gravity fields and electric fields and about potential energy fields?
Okay, but so you're saying that, but if you're equating weight and gravity as the same thing, that's not the same thing as an electric field. So you're changing the definition across three.
Both, okay, it's not the same thing, but they're both potential energy fields.
So a weight field is the same as a potential energy field.
It is a potential energy field. It's not this. That's what it is.
So weight is a potential energy field now.
Correct. Well, it always has been. I mean, when something has weight, what it's to say is to say that it has potential energy. That given the absence of all other forces, that it will, or all other retarding forces would be the word, it will fall and it will go into one direction. Yes, it's a potential energy field in the same sense that a charge in an electric field is a potential energy field, in that it will move towards each other if they have opposite charges, or they'll move away from each other if they have like charges.
Give me a minute, I'm thinking.
Let's work.
So how did the weight get up to be able to do work?
Energy. It had to have energy, and the energy from the outside source in this case is the sun. So the sun heats up the air molecules, which then increases the amount of energy that it has, which then allows it to do more work than what it normally would do, and so it goes up.
It has less weight.
But without the sun as a source of energy, the molecules would would condense, and they would get what's called clustering. So there's this idea of gravitational clustering. And there is, you can look this up. You can look up just look up gravitational clustering and entropy, and you'll see stuff out there about this and about how when things are clustering together under gravitational influences, you're actually increasing entropy. And you have to be, because that's what's happening right now in the universe. So entropy can't possibly just be going down. It has to always be increasing.
Wait a minute. So cause like when you
You're a robot. It's hard to hear what you're roboting. Maybe you have to back out and come back in.
Now?
Not really.
Can you hear me now?
A little. It's kind of loud though.
Yeah, I'm driving, so it's hard. I can't get rid of the background noise. Is that better?
Yeah, it's okay. I think we can keep going.
So is it the gravitational forces that causes, when you cool down water, that causes it to come together to form ice? Is that the gravitational forces, or is it the bonds?
To form ice? No. It's a loss of energy, but that's
Covalent
there's
bond,
multiple things going on there.
Clustering.
Okay. So it'd be something to do with bonds within the molecule.
Well, why does ice turn into water? Why does water turn into gas? It's all about those coulombic bonds that are separated. When you have pressure holding the air together, it's pushing together.
Danny,
those bonds.
Are you Danny Zanuck? I was talking to Danny. Actually.
But he's actually good at answering that. That's actually, I didn't even quite that is correct. When the energy of a molecule, the average energy of a molecule, is larger than the energy that is keeping two molecules together, which are covalently bonded. Or actually, are you sure it's covalent in that case? Coulombic, yeah. I was going to say, yeah. So the coulombic bonds, because they're not perfect. There's a dipole moment for a water molecule. It's not, the charge is not evenly distributed because the size of the atoms.
Right.
So then they bond together, but when the energy is large enough, then they can go into a water state, a liquid state that is, or a gas state, depending on how much energy they.
Think about it like a cartoon. Think of all these little molecules that are all being pressed together due to this air pressure. And when the air pressure is reduced, and they're at a certain temperature, they're moving at a certain rate and they're running into each other. And finally, they can break free from each other. That means that becomes a gas then. So if you think of it that way, like a cartoon picture of these molecules moving around and breaking free one another so they're separate and not bounded together by this pressure, that pressure that bonds them together and creates this bond is broken. Now it's a gas. And you can take it a step further. They get aligned in perfect order when they get really pressed together. And that can be a temperature change.
In all those scenarios that you described, most of the things have got to either be contained for them to be pressed together or the temperature to be reduced. If you remove the temperature of a particle or remove its so-called mass or its weight, what will happen to the pressure under those conditions?
If you have change the temperature, yes, you can remove temperature and have those molecules go slow down and then organize themselves and form a solid. That's called ice, right? And so it's
What's
ice.
the pressure
liquid,
value?
gas.
What's the pressure value? What's the pressure of that gas?
Well, 32 at 0 degrees Celsius, and at standard atmospheric pressure, it will become ice.
So what's the pressure value?
29.92 inches of mercury.
So if you condense all the gas in a container by reducing the temperature inside that container, what's the pressure inside that container?
I don't really understand your question. I'm saying, I just told you, if you have 29.92 inches of mercury and you lower the temperature to 0 degrees Celsius, it'll change states from liquid to ice for water, H2O.
Okay, so what would be the pressure inside that if it's all of a sudden all the gas inside that container has been reduced to a solid? What would be the pressure inside that container? Right? If all the molecules have been reduced to a solid, there would be no pressure in there, right?
Oh, I see what you're asking.
The pressure of ice.
Yeah, he's asking what the pressure inside ice is.
No, inside the container. I'm talking about the container.
I'm giving you the answer. If you have a container full of water liquid and you took it down to freezing, then the pressure inside the container where the ice wasn't, so it's obviously reduced in volume. Say it starts with a gas and then it goes to ice. You would then have the vapor pressure of the ice. So you would still have a pressure. It's called the vapor pressure. Ice does have a vapor pressure. It does actually give off. Can still sublimate and go straight from ice to water vapor.
So what would be the temperature? Still haven't answered the question. So what would be the temperature or the pressure inside that container?
What was the
vapor pressure of ice?
Okay. So maybe it wouldn't be 14.7 psi anymore, right?
Check.
No,
yes. See, we went over this yesterday too, Paul, regarding like boiling in a pressure cooker that didn't leak. What happens to the
stick to his question.
Yeah, don't go off on a tangent.
No, we went over this for 2 hours yesterday about boiling water and what happens with the pressure. But go ahead.
I still haven't heard an answer. I'd like to hear an answer to Paul's question.
The vapor pressure of ice. If you had a gas full of water and then you froze it and it formed ice, then the pressure in the container would have the vapor pressure of ice at 0 degrees. It will vary according to temperature. If you have it at 0 degrees, the vapor pressure will change with temperature. But if you have it at 0 degrees where ice forms, then the pressure in the container will be the vapor pressure of ice. In other words, ice will not necessarily always remain as a solid. It still can sublimate because there's no pressure. It will actually still be ice. There'll still be water as a gaseous form in the container because
No, it's okay. I knew that. I actually knew about sublimation. Actually, I know a lot more about chemistry and how gas give me credit for, by the way, because I took chemistry in college and also worked with air conditioning in the Air Force. So I know a lot about how gases turn to liquids and liquids to solids and all that fun stuff. So my simple point was, if you remove the temperature enough, the pressure inside that container would reduce because there's less gas and less heat inside that, correct?
If you're reducing the temperature of a container with gas in it, for example, say a gas and a liquid inside of a container, you're asking what happens to the pressure as you lower the temperature? The pressure goes down.
Yes. Okay. So it has been demonstrated. Good Times for All has done this. He's had one container, and actually created a differential pressure inside of a container using heat and cold. Heat on one side and cold on the other. That's possible. So you can have a differential pressure inside of a container if you have the factors of reduced temperature or even reduced whatever the mass, if you want to call it weight or whatever you call it, of the so-called gas. You can also create a differential pressure. But even to have that differential pressure, you still got to have a container.
No, that's not true at all. All you need is a force, Paul.
Yeah.
This is proven many times. They use this concept, this idea. You said you had experience in air conditioning and heating systems.
Gravity is not a force.
You're talking over me. You would know this then. All you have to do is accelerate that. And centrifuges do this all the time, by the way. They create pressure via...
Okay, so the Earth is a centrifuge?
No,
what you're saying?
Forces. Doesn't matter where the force... Here we go again. Doesn't matter where the force comes from. It matters that there is a force. Now, if air has weight, that's its force.
How did you determine that air has weight? How did you determine?
You can measure it. You can weigh it.
You can put air inside of... Hold on. You can put a vacuum chamber. Hold on. Cody's lab has done this. He put a vacuum chamber on some scales. He then removed the air from it, and it weighed differently. So he was able to work out the mass of the air that was in the chamber. Very simple.
Okay, so there's a... Hold on, Rumpus. So basically, the only way you can weigh a gas, it has to be contained of some kind, right?
No.
That's irrelevant. Hold on. Whether or not gas has mass. And I've just shown you how it does. If you go to a second question, first you haven't accepted what I told you. First of all, we've got to stop at the point where you made the first claim. You've been given an answer. Do you accept it?
Well, the only way you can have to weigh a gas, it has to be. So you have to have some kind of container.
How you do it.
Yes.
The question
you rumpus. You can't rumpus. You can't rump.
I can mute you, Rumpus, by the way. So just remember that.
So be
I can
quiet
give
just for a
you.
second. Be
It
quiet.
doesn't
Just
I can.
matter how you weigh something.
Rumpus, calm down.
It matters whether you've done it or not.
Okay, I can give you an example, Paul, where that doesn't happen, where you don't need a container to weigh the weight of air. So if
How?
you have, okay, so if you have a syringe and you have the, the stopcock or whatever, the cork, and you have the syringe in a position where there's, you squeeze the syringe so that there's nothing in it, right? Like but there's still air on the backside of it. It's kind of hard. I guess I'm not explaining this well. But you know what a syringe looks like, right?
I know where you're going, Danny, and I get what you're saying. I even get what Rumpus is saying. But the only way to weigh something is it has to be contained. Shut up, Rumpus.
That's not true.
Shut up, Rumpus.
Why
You
are
can,
y'all
okay, let me put it
rumpusing
this way.
Paul?
Let me put it this
I'm
way.
done.
I actually think I know a better way to phrase it.
Three people just rumpus Paul.
Well, I wanted to explain it. I wanted to get my point. Okay, you can weigh a syringe when it's closed, and then you can pull a vacuum in the syringe and weigh it again. The first time you weighed it, it'll weigh more than the second time. Now, the first time you didn't have the air wasn't in a container. The second time you pulled a vacuum. So no, you weighed the air without having it in a container in that example.
It doesn't matter how you do it. Paul challenged whether or not gases had mass. Way of establishing.
That's not what I said.
And remember, another way
Don't
also.
misrepresent me. I didn't say that.
Okay.
I said the only way you can weigh a gas is it has to be contained or under pressure.
Remember, we know that mass has a property called inertia. So if we have a volume of mass or a volume of air, and we can actually measure its inertia, we can then extrapolate and give it a factor for how much mass it has. And any mass we can measure has a weight. So we can do aerodynamic tests with air to find out what its inertia is. And if we know its inertia, we can then determine what its mass is.
Are you accepting that gas, like air, has mass or not?
That was my leading question for that question.
What's
Thanks.
mass? Define mass.
Any amount of matter.
Right. Well, no, mass.
Any amount of matter.
I agree based
So I
on
have one
density,
electron.
it
That's
can
an
create a
amount. That's
downward
an amount
vector.
of
Yes,
matter.
yes.
What's the weight?
Let me take this, guys. Any amount of matter. Yes. Electron
Okay,
is
let's
mass.
talk about weight. If you prefer, let's talk about weight. Do you accept that gas has weight? We'll avoid the subject of mass for the moment. Do you accept that gas has weight?
Define weight, and we'll talk about it. Define weight.
Mass times a force.
Hold on. You can. Some scales. Scales measure the weight of things. If I put some gas on some scales and then I move the gas, I get a difference in what the scales register as the force upon them is the gravitational force, which is defined as the weight of something, is the gravitational force. So removing the gas or putting the gas back in shows you the weight of the gas. Do you dispute this?
Except for the gravitational force part.
Right, so you do agree that gas has weight now. So while you were questioning this earlier, or perhaps you've just had a revelation now that I've explained, you now accept that gas has weight. Is that correct?
I didn't say that. That wasn't me, by the way. All I'm saying is the only. Go ahead. If everyone wants to talk over me, go ahead. I'm done, by the way. Go ahead. You guys have fun. I keep getting talked over.
No, Paul, you was leading.
Yeah, Paul. Paul, do you accept that? I think it was you. Do you were questioning whether or not gases have weight? So do you now accept that gases have weight?
I mean, on the way, there is an equivalence between pressure and weight. Because if you have less pressure, there's less pressure, there's less weight. So if you have a vacuum pressure, that's less weight on a scale.
Right. So are you saying you don't accept that gases have weight now? Yes
I think there's an equivalency that you're drawing between weight and pressure. Because if you remove all the pressure from the container, whatever you're using, there's less weight there. You increase the pressure inside the container, the weight will increase. So why is there just pressure?
You don't get pressure for free. It has to be exerted by something. In the case, it's atoms that exert pressure. Something to exert something to have pressure upon you. Although I suppose you can have electrostatic pressure, I suppose, or magnetic. even then that still has to have some sort of atom or something to act upon. So yeah, I think I'm probably correct. You still have to, even in the case of fields, they still have to have something in the field for it to interact with. But certainly in the case of the kinetic theory of gases, which hopefully, perhaps you're disputing this, they have mass and they have weight. And there's an experiment you can do to show that the air has weight. But the pressure is a side issue. The stuff that gives it weight is not the pressure. It's there has to be something in there with weight to exert a pressure, and you can measure the weight with scales, and you can measure the weight of some gas.
You're saying there has to be a downforce.
Yes, that's what the scales measure. Scales are force measuring devices. They only measure a force. That's all they do. And when you put them on the floor and you stand on them, you measure the weight of what is on them. But if you
see, I don't know if you got to put that word on it. They only measure force. You could say they only measure that phenomenon.
No, they don't just
no.
measure
How
that
can you
phenomenon.
say no to that, Rumpus?
Well, if you get me on, so I'll explain to you. If I pick up the scales and put them between my hands and press on them, they will then show the force that I'm applying with my hands.
But I'm saying you're defining it as a force. It may be a little too rigid. I agree.
Let me finish my sentence. So there are force measuring devices. They measure the force that's applied to them. That can be by your hands, you pushing them up against the wall, pressing them between your hands, or using a vice on them. Whatever it is, those scales just measure force. It doesn't matter where the force came from, whether it's the result of gravity, you push them with your hands, or we're using a vice. They just measure force. And it just so happens that when you just leave them on the floor and you stand on them, the force that's exerted on them is your weight, which is caused by the gravitational force upon you.
You're fighting it, Paul. Just kind of let go and accept the force, because that's the answer.
Yeah, Rumpus wants to box in his definition of force. I mean, if he wants to do that, God bless.
Is the accepted scientific definition of a force is what the springs inside.
I agree, but when you start wanting to argue what the cause of that is, okay, lines are going to get blurred with your words. I'm telling you.
You were disputing that scales. You said
I didn't dispute shit. What I don't. You interrupted Paul. You interrupted him.
When I said you press them together, you said no, scales are specific to do measuring. No, they're not.
I didn't say that.
Oh, sorry,
I said it's a phenomenon. It's still a phenomenon. They're measuring the phenomenon of you pressing your hands. If you want to call that a force, call it a force. It's going to limit you in future conversations of your definition. That's all I'm trying to say.
Scales just measure force. And I think it was you who said that they were specific, had a specific function or measured a specific sort of force. No, they don't.
That wasn't me.
They measure mechanical force that's exerted on them. And that mechanical force can come from anywhere, whether it's me pressing it with a vice, my hand, standing, poking my head out at it, holding it up, pushing on someone else, pressing it up against a wall, or standing on it. All the scales know no difference between any of those activities. They just measure the force that's imparted upon them.
Cool. You're clarifying what you mean as the force of weight. And it's funny because... Go ahead, man.
I just explained to you that scales measure any force, mechanical force expressed upon them.
And then you want to say what the cause of the weight force is.
Yes,
you're saying it's the gravitational force. I'm agreeing with everything you're saying. I don't know why you're interrupting Paul.
You were disputing. You said they were specific or something. I'm sure it was. I thought it was you. Okay, perhaps I'm wrong. But the point is that scales are just force measuring devices, so that we know when we stand on them that there's a force being exerted on them, because they show that on the scale. So we know there's a force being exerted by you downwards on the scales, and we call that your weight, and it's caused by, and we also equate that the force of gravity we call your weight by definition.
Right, and it sounds like that's like second grade shit, and it seemed like Paul was trying to get us to understand a deeper correlation with pressure for some reason, but you didn't let him give. Okay, if it's we haven't even heard it yet, but it's irrelevant. All right.
Pressure isn't weight. Pressure is scalar. Weight is vectorial.
All right, get excited.
Actually, pressure. It's. Actually, no, you're right. Actually, it's because it's defined by a square. It's divided by a thing. There are arguments over whether pressure is a vector or not, but yes, it's generally accepted as a scalar. Actually,
right.
But there are some slight questions about it. But the point is,
in Danny's syringe. Hold on. In Danny's syringe, Was there less pressure when he pulled the syringe out? Was there less pressure inside the?
Yes.
Did it weigh less?
Yes. Oh, yeah. Way less.
So there's a direct correlation inside of, when gas is inside a container, whether it's pressure, I can't even talk straight, with how much pressure is inside that container will determine the weight.
The pressure's just telling you the stuff in there. That's all it's doing.
I misspoke. I didn't know the situation. No, when you have a syringe and you have no volume, then you make volume with the syringe. It doesn't change its weight at all.
Yeah, exactly. I thought. Yeah, I didn't agree with you. I'm glad you corrected yourself.
So if I pull the syringe out, there's more volume. What's the weight of the syringe?
Right, if it's sealed, if the syringe is sealed, it hasn't changed weight at all.
You made a vacuum. Remember, no masses inside that chamber now.
So if the syringe is closed, right? So nothing can enter the syringe, and you have it. So if you have your syringe on some scales, it weighs X, and then you
can you show me this? Syringe, can you show this to me? Please? Can you show it to me? Just instead of talking about it, show it to me.
Were you ignoring buoyancy intentionally?
I'm not. Did I ignore anything? I did not ignore or I'm just bringing up questions, bringing up points. You just, I'm asking.
Whoever mentioned buoyancy was correct, because actually, if you want to get into details, everything because the air around us causes a small buoyancy force. If you increase the volume of something, you do actually cause the buoyancy force of the air. This is why when you measure things and you go to a physical laboratory, they measure everything in a vacuum to avoid any buoyancy effect. So if you increase the volume of your syringe by pulling it out, it actually will seem to be lighter on the scales by a very small amount, caused by the displacement of the air that the other end of the other end of the syringe, the knobby bit. You've actually pulled out a bit of a bar of the syringe, and therefore you've displaced a bit of extra air. So actually, it will weigh slightly less. But if it's in a vacuum, it wouldn't. If you have a vacuum chamber and you made these measurements, it wouldn't make any difference. But whoever mentioned the buoyancy, there is actually a small buoyancy effect, so they were correct. I think it was them.
Can I say something?
Yeah.
Cheek posted a real good video for anybody on Entropy. I don't know what the name was there, Cheek, but if anybody interested, you should make sure you watch that movie.
Which one is that?
The Second Law of Thermodynamics, Episode 4, Introduction to Chemical Change in Thermodynamics. Professor George Porter.
Did you post it?
It's in the live stream.
Steve?
Yeah, Zanuck, I watched it. No, it clearly explains from a scientific view definitions of entropy, and it'll clear a lot of things up for everybody.
Can't you put the link in the live chat? Is it not possible?
Yeah, I don't see it.
Chike put it in there. It's up there.
A long time ago?
But if someone knows
from an hour and 10 minutes ago, hour and 20.
Right. Yeah, this is a good. Yeah, this is about. This is Eric Porter. This is the one that Fug XD has just posted. That is Second Law of Thermodynamics. That is a very good video on there. That is a very good video. Actually, there's some interesting angles on things that it actually made me think about something in a slightly newer way. That's a really good video, actually, that one.
And exactly an hour ago? I can't find it.
It's been posted again by, I presume Fudex has just reposted it, I presume. Is that the one?
Oh, yeah. I've watched that many times.
That's an excellent video.
Yep.
And I can't remember, there was one revelation for me that I emphasized again that I'd not been thinking about as hard as I should have been. I can't remember what it was now.
Well, the one thing that I've never really given much thought about was in the reversible. I mean, you and I started that. You started that.
Yeah, that's right.
And so I started looking into it because in your mind you have an intuition, you have things you've learned, and you want to be able to apply it to any process. And you can start looking at reversible or non-reversible, and then look at what is actually happening. And they don't ever talk about in a isentropic reversible process versus a free expansion. What happens to the temperature? They talk about that, but they never talk about what's happening in the pressure. And that's a way to really understand what's happening in free expansion. The pressure went down, right? Even though the temperature stayed the same, pressure went down there, and they can do all the calculations whether they both Boltzmann or Clausian with that information. And the same thing happens with the reversible. You start breaking it down. What's volume expanded, the gas expanded. What happened to the temperature? Oh, the temperature this time went down, whereas before it didn't go down. Well, that's interesting. What happened to the entropy? You do the calculations. So you always can use all these calculations in any situation to determine what happens with the energy unavailable to do work in a system. And that's what entropy is.
Because you were also being a little bit confused about the work. You were saying atoms were hitting themselves, but
I was trying to get into the microscopic level. What's happening, like all the individual entropies.
But the point is, you can't do work on yourself. I mean, that's the key thing.
Right? Yeah. No, you're right. No, that's why I kind of got to a kind of a come to Jesus meeting with you on that. And like, okay, that's really not.
It was just a pity that QE was around to watch that too. You see. Yeah, he's such an idiot. We really must do a video on what an idiot this guy is.
All right, that's enough of that. That's enough.
Well, look, when he comes out and blatantly says, "Hey, the reason that air expands is entropy. That is the reason. Air goes from high pressure to low pressure because of entropy." And that's just not right.
Yeah.
As I showed earlier.
Yeah, the high pressure causes a change in the movement from a high to a low pressure causes a change in entropy, because entropy is a state of the system. It's a property of the system.
It's a property. It's a state. It's a state property.
Yeah, state property.
State function.
Yeah, state.
All it is. It's not a reason. It's basically an observation. Like, what happened? You did this. You did that. What happened? And they do measurements.
I called it a perspective too. Remember, I said it's a perspective.
That could be. Yeah, you can look at it from that way as well. But as long as you know that's not a force. And then he goes, "Oh, what about?" He does a quick search. You can here's his head smoking, and here's smoke coming out of his ears. He does a search, entropic force. Oh, I found an entropic force. There you go. There's my answer. No, read what entropic force really means. It's a statistical tendency. That's not a force at all.
He never understands his citations. He never understands. He just simply picks out a phrase, links it, and then you always find, just like Gleason, the citations he has contradict himself.
Well, who are we talking about?
QE.
Oh, wow, he's not here. Let's move on.
Paul, were you?
Are you? He talks about people who are not in the channel constantly, non-stop.
Doesn't make it right. Doesn't make it right.
That's what we have here, though, Raki. Nonsense. He mentions my name 1,000 times a day.
Doesn't make it right. Let's move on.
Are you going to stop him if
it makes it funny, though.
It does make it fun. I don't mind him doing it, by the way. Hey, by the way, so someone tried to correct me with entropy not being a law, and he had all these posts about entropy being a law, right? Try to prove me wrong. Right?
I mean, it's a direct property of the law.
No, people.
Anyway, can we see where Paul was going? Because I wanted to ask you guys something. If he was kind of at an end to that.
Well, the point was about citations. You can find citations, and that's why I kind of was. Effectively, Rumpus and I were kind of at odds about this a little bit, because I was saying, the kind of a slang of entropy is it's entropy law of entropy. It's slang, and people talk about that, but it's not right. And Rumpus was absolutely right. It's not a law, and I was agreeing with him. But I was saying, but we sometimes call it that. Well, then all of a sudden, everyone comes up with these posts. I gave one to Rumpus saying that the law of entropy is actually a definition. But if you look at it, if you read it, it's some guy's blog. Now, just because someone else uses it incorrectly and puts it in print doesn't mean it to be correct.
Okay. You've got to make sure your sources are from scientific institutions and not just somebody who's expressing an opinion.
Yeah, go to the university site. When you go find it from like University of Pennsylvania, physics department, and it says the law of entropy says then we will listen to you. But when it's some guy's blog, you're not going to get much attention for that.
Sure, they're two separate issues. One issue is you're saying it doesn't do what he says it does, or it's not the responsibility for it. The second issue is you're saying he's over-asserting the slang. And I mean, look, from one perspective, it is used as slang. There is a law that it's directly correlated to as a measurement perspective of. It is something that's always happening, right? I mean, entropy is always happening, right?
It's not a law. It's not.
Okay.
It's a property.
Thermodynamics. Thermodynamics isn't a law.
It's a differential property of the second law of thermodynamics.
Of a law. That's what I'm saying. It's that, right?
It's
it's a property of a law. Okay.
It's like saying inertia is mass. No. It's a property of mass, right? You can't say inertia is mass just because they're related. And by the way, he misquoted me again saying it.
No, you say inertia is a law, though, because mass is a law.
There is a law of inertia.
It's two separate issues. It's all I'm saying.
But there is a law of inertia.
Yeah, that's the first law of Newton's first law of motion.
Yeah, there is a law of inertia, but I'm talking about
inertia is equivalent to mass. In almost all circumstances, we can equate inertia with mass, and that's how you measure mass. When someone was talking about earlier about what is mass,
Right. So I'm just saying,
you can't do that with the second law. So
don't worry about
inertia and mass.
Over assertion of the slang. It's not.
They're not the same thing, though.
Sure.
We're gonna have to discuss this, Anik, because I think you'll find that.
Yeah, y'all might want to get together. Y'all know this is being recorded,
That's
right?
fine. That's fine. He can record all they want.
I'm just saying, y'all might want to get together later.
Inertia is a property of mass.
It's a property of matter, just like the mass is a property of matter. Inertia is not a property of mass. Inertia is a property of matter. Mass is a property of matter, and those two properties are actually effectively.
Mass is a property of matter.
Mass is a property of matter. Yes. Not all matter has mass. I don't think that.
Not all matter has mass, really.
I might have to. I'm gonna.
You have to look that one up. Yeah.
Yeah, but the point is, different sorts of matter has different sorts of mass, but it's a property of matter.
Inertia is a property of.
No, it's not.
It's not. Go find me a citation on that.
Well,
mass is a physical quantity.
Inertia. When you apply a force to something, it will respond with a certain acceleration.
Right.
That's its mass, and it's also its inertia. That's how we define the mass. That's defined by forces equal to mass times acceleration. That mass is the how we define mass improperly. And so it's the force divided by the acceleration. That's how we find the mass of something. On this ISS, for instance, where they do not have a weight system, what they do is they measure the mass of the astronauts by exerting a force on them with a spring, and then seeing how quickly they accelerate. And they measure the mass of the astronauts. That's also their inertia. We'll have to perhaps have a little discussion about this, but no, inertia is not a problem. Mass is a property of matter, and inertia is a property of matter, and they're effectively the same thing.
Mass is made from matter. Mass is the amount of matter.
No, it isn't. You can have.
Of course, it is.
No, there's different sorts of matter has different sorts of mass. No, it isn't.
No, mass. Okay, hold on. Mass is any amount of matter. Its unit of measure is the kilogram. Mass is any amount of matter.
And the kilogram is defined as what happens when you exert a force on something. The mass of 1 kilogram, you have an acceleration of 1 meter per second.
Inertia is described as its resistance to acceleration,
which is what the same as mass. That's what
it's a property of it. I mean, we're getting pedantic in our definition, but I'm not
incorrect. Inertia is effectively equivalent to the mass. The only time it's different, inertia is defined as the resistance to a force. In other words, it's the same thing. It's force divided by the acceleration.
I know. So is inertia in terms of kilograms?
Yeah.
Okay. So there you go. Now, why do they even have the word inertia if its mass is inertia?
Well, because they started off with and it's an old word, inertia, as a general property of how something resists a force and how much it accelerates. And then they decided, because you see, put it like this, you could say, imagine you had a mass on a spring. So there'll be some additional resistance. If you could say the inertia of this thing on a spring is not only the mass there, but it's being held back by a spring. So actually the inertia of that body with a spring would be different to its mass. But for a free body, mass and the inertia are the same thing. Because the inertia is defined by force divided by acceleration. That's also the definition of mass. Because the resistance to a force, the body's so I'm like a bus in space. If I push on it with a force, will move very slowly. If I push on a tennis ball or something, it'll go faster. That's defined as the inertia of that object.
Yeah, it's resistance to acceleration, correct.
Yeah, so that is exactly the same definition as its mass.
I don't agree.
Why don't you agree?
I just wanted to disagree with Rumpus.
You wouldn't want to change a habit of a lifetime, yeah. I mean, you want to be wrong all the time. I know that. If you want to disagree with me, you're definitely guaranteed to be wrong. There's no doubt about that. If you want to bet on anything, you can bet that I'm always right. The rule of the internet is that I am always right. So that'll help you a lot.
The rule of the internet is when someone says they're always right, they're probably not.
Probably not, but in this case, it is. That doesn't work. I'm the exception to that rule.
You are an exception to the rules, Rumpus. I'll give you that.
I'm glad we're agreed on that. I'm not always completely right, but God, I very, very rarely make a mistake. The point is, I don't speculate. If I don't think I'm right, I'm not firm about something.
Yeah, he's done it with me plenty of times. You hear him here all the time. We go back and forth, and I'd say probably 70% of the time he catches me on something. I get him.
Oh, one of the most humble guys I know.
Well, this is not tough stuff. Rupert and I laugh at this because this is high school physics that we're reliving.
It's so easy to be right about this stuff.
Yeah. Right. So why the fuck are we doing this?
But definitions are important. So we're trying to make it very clear for people that don't know physics. So we're trying to stay very accurate and be able to explain where they come from, the root words of these terms, where they came from, what do they mean.
Yeah, I mean, that's absolutely right. It's very.
I have a question for you, Xanax. I'm sorry.
It's very easy to be right about stuff. Karen Recker.
Xanax, I know you agree that we can have. You say that we can have gas pressure without a container, right? You agree with that?
Yes.
I disagree, but that's okay. So, have gas pressure without a container. How do you measure it?
The usual way you measure pressure.
With a barometer. A barometer. A pressure sensor. Anything that can measure the force around it. Anything you can measure those individual atoms or molecules making contact and hitting a surface, creating a pressure, a force per unit area.
Okay, I understand. So without the surface of a container, they're colliding with themselves, right?
Correct.
They exert pressure on themselves, yeah.
And that's the only thing.
This is the question that QE won't answer. I keep on asking Q this question. In the middle of a room where there's no walls, is there a pressure there? And he won't answer that question because he knows how it exposes his idiocy.
Can I address something to Zanuck real quick? I've actually heard Zanuck say that the proof that gas has weight is a barometer. Did I hear you say that correctly at one point,
yes.
Zanuck? Okay, so back to my pressure thing.
That's an odd thing to say, Nick.
You might want to get with Rumpus on that later, Zanuck.
It's mass. They've got to have mass to have a pressure. You don't have to have weight.
No, but the proof that air has weight, according to Zanuck, is a barometer. So that's pressure.
Well, hold on. But for instance, if you went out into space, the molecules would have no weight because weight is defined as the gravitational attraction to a planet or whatever planet around you, or nothing that's gravitationally pulling. Things do not have weight. So a bus in space or a tennis ball in space float around in the same way. They don't have any weight, but they still have mass.
I see where he's going, Rumpus. Yeah, he's got a gotcha going here. So yes, Rumpus is right. And then you go into space and you create pressure not by its weight, but by compressing that air into a small container, a tank. So why does air having weight create pressure? You've created the pressure with the container, right? Right, Paul?
So air would float around the astronauts when they breathed out?
Paul, I'm talking to Paul. This is a real quick conversation. And a good one, too, by the way. Paul, great question. So remember what I said before? I said, yeah, barometer is a quick check. I said that air pressure is caused by one thing, a force. That force can be caused by a container's walls, or it can be caused by the weight. I was very clear about that. So don't just take one thing that I say, cherry pick it, and then use it against me, because that's not going to work.
This is a classic case, Zanuck. There's two causes. They can't cope with more than one.
Hold on, Rumpus. You actually said that the barometer is proof that air has weight. That's what you said.
Because there's no container. Right.
On the Earth, it has weight. In space,
if I put a barometer on the space station where there's no gravitational force, would that barometer work?
No. Oh yeah, of course it will. Yeah, and it will give you a register, but it won't show the air has weight. It just shows that there's.
So you're using a barometer as a false equivalency. That was my ultimate.
I know, Paul. I know what you're going to say before you say it. Trust me. So yes, you're using on the Earth. You have no container, so we're now putting two and two together and realizing that the weight is causing this pressure, not the container. Now you're saying if we don't know if there's a dome or not. That's a good question, by the way. We have the barometer in the space station. Hold on. We have the barometer in the space station. It measures pressure, but the air has no weight. We measure the barometer on the surface of the Earth. It shows the pressure, but it does have weight. How do you know? That's a great question. We have to take it to the next step then.
Is the space station a contained system?
Yes, I'm agreeing with you, Paul. It doesn't have weight in the space station.
Oh, I'm done.
And it's caused by the container. You're right. I think it's everything. Everyone knows here that if we have a container and we heat it up or pressurize it with the gas, we can create pressure. Nobody disagrees with you.
What we, as Zanik said, the pressure that exerted by the gas is the collision of the gas molecules with something that measures pressure. But the question is, where does that the force of those things come from? And what people don't understand about the atmospheric thing is that there's a force. In a container exerts a force to contain a gas, but the gravitational force does the same job. And of course, we only see these things on the large scale because gravity only becomes important when you have large things.
Sorry, Rumpus, we have the. I'm sorry. Go ahead.
You're only on the Earth, but only because we're near the Earth do we have these gravitational effects. And the Earth's gravitational pull is one of the very few properties that acts on mass. So, for instance, if you've got a neutrally charged atom, like a molecule of oxygen or something, how do you pull on that? Well, gravity is the only way to do it. It's the only force, except for bashing it mechanically with another gas molecule. The only way we can exert. Oh, let me nearly finish. The only way you can pull on that oxygen molecule is with gravity. So that's why we've got this special circumstance of requiring an Earth, because that's the only thing that can exert a gravitational force. Nothing else is big enough. And
that might be a good segue, man.
Real quick, wait for Paul. You still there?
He said he was done.
Paul, I'm done. You guys can have fun. Go ahead.
I have a quick. Can I ask you one thing?
I love this transition.
Paul. This is why I need to jump in, Paul. Here's the main reason. The elephant in the room. Now we have a pressure gradient inside the space station. Gradient in our atmosphere. So what causes that? If we had walls of the container causing the pressure like we do in the ISS, we would not have a pressure gradient.
Except for this segue that I'd like to bring up. Maybe we can get to
still talking. Don.
Yeah, I know.
It's a very important point. Don, very important point. So
I know, high school physics, important point.
Yes, the reason we know that we have air pressure caused by its weight is because we have a pressure gradient, and that cannot exist knowing gas laws and knowing the laws of atmosphere without the air having weight, in which Rumpus eloquently said air does have weight because we can measure it because it has mass. That's why we have a gradient, and that's why we have air pressure.
I'm glad you know all the laws of the atmosphere.
Zanik, let me ask you, where is gas pressure's weight or mass, whichever one you want, you call it weight, right? Where is gas pressure's weight more at its highest, at ground level or in upper atmosphere?
Gas pressure and its weight will be the same. The weight is always the same.
Someone's got the TV on the background. Turn it off.
Unless you want to measure the weight at much higher altitudes where the gravitational force or their weight changes. But let's just talk about, I know what you're asking. The pressure is greatest at the surface, as you know. And it goes down precipitously as you go up from 14.7 psi to
right. But is the weight the highest at the ground?
Yes, air's weight is the highest at.
Why does it ever go up?
Why does it go up?
Yeah, if the weight and mass of gas pressure is the heaviest at the ground level, why does it ever go up with the gravitational pull being the factor?
Why does it never go up? I don't know what that even means.
Right. Well, in other words, he's saying, why doesn't everything form a pool at the bottom of the thing? How has it ever managed to get up to 63 miles high? And the answer is that the gas molecules are moving around at a few thousand miles an hour. And the key thing is, it's not like our world where things lose energy through friction or whatever. Gas molecules do not lose energy. When they hit one another, they hit one another's cells perfectly elastically. Energy does not disappear. It's not destroyed. So when these things are moving around 2,000 miles an hour, imagine if I threw a ball up in the air at 2,000 miles an hour. Imagine how high that would get. It would get up to about same level as an oxygen molecule would, 63 miles up. And they're subject to exactly the same thing. So
okay. Fair enough, Rumpus. So each gas molecule has its own weight, and it moves freely at that miles per hour, right? In all directions. Why does it stop? Why does it not keep going up and fill the available volume? What stops
What's
it?
the thermosphere? What's the thermosphere?
Because
It's the highest
because
levels of the atmosphere that have the highest.
What stops it, Rumpus?
I'm about to say, when you throw a ball up into the air,
Don't do the ball. Do the gas
no,
molecules.
it's equivalent. It's exactly equivalent.
Why
That's why I'm using it.
equivocate? Use
But
gas
I'm explaining
molecules.
it. If you give me a chance to stop interrupting me, right? So when I throw a ball up into the air, if I was to throw a ball up at 2,000 miles an hour, it would go up very, very, very high and eventually come to stop and then come back down again. Gas molecules are exactly the same. A ball is, for the kinetic theory of gases.
Gas molecules are not like a ball you throw up.
They're exactly like balls.
They have mass. Yes, they are.
Yeah,
Right.
but they're not moving freely in all
just say
directions.
if you threw a molecule up. I mean, come on.
Gas does not move freely in all directions either. Gas has
finish my
weight.
answer, please? Can I finish my answer? In the kinetic theory of gases, which is accepted by all of science, we can treat the gas molecules exactly like balls. And just like when we throw up balls, they come back down. Similarly, the gas molecules, except the balls are subject to resistance and air friction, which are effectively gas molecules not because they don't have friction, because they preserve energy, whereas balls. What's the difference?
So not exactly like gas molecules.
In the regard that I'm talking about, the kinetic theory of gases, if you remove the friction forces, they behave just like gas molecules. And if you throw one up at 2,000 miles an hour, that's exactly what a gas molecule is doing.
Yeah, but the gas molecule is moving freely in all directions.
That's why you have escape velocity. Unless you have escape velocity, those molecules will come back down.
What stops those gases?
I could throw a ball in any direction. Yes, I could throw a ball in any direction. I could throw a ball horizontally, vertically, 45 degrees. And the gas
How about
molecules
this assertion of escape velocity? Do we have a escape velocity was discovered and proven?
Basic physics. You can work it out very easily.
So no or yes? Do we have a scientific citation to when it was discovered and proven that
Why
something
does it matter
can
when
escape?
it doesn't matter if it's
Yes or no?
yes.
Just a simple yes or no for the audience. I just want to get it on the record.
Doesn't matter when it was discovered. It could have been
So
discovered
no or
yesterday.
yes?
Just let me
So we
answer
don't
the
have the
question. I'll answer the question yes or no. But first of all,
I'm not going to accept anything other than a yes or no.
Well, you're going to have to. Right.
No,
so
that's bullshit.
Well, okay, we'll be
It's
quiet
a
then.
simple yes or no question,
Well,
Rumpus.
I will answer yes or no. I personally don't happen to know the exact date that the maths was done, but it doesn't matter if it was done yesterday. It's correct. If someone worked out only yesterday, that doesn't change whether it's correct or not.
Do we have any citation? Can anybody provide a citation of when escape velocity was discovered and or proven?
I can't.
Well, I suspect it was in the 19th century, if not earlier. No, in fact, Newton did. Sorry. Of course, Newton did. Yes, so Newton would have...
Newton made something escape the Earth permanently?
No, you asked when it was worked out. You didn't say...
No, I didn't say when it was worked out. I said when it was proven that it's a thing, that you can have escape velocity, period. When it's been proven. When have we seen something perfectly escape the Earth? I appreciate you entertaining. I did want to segue into some other stuff, and I had two kind of tiny, quick ones. When you guys are talking about something in space, would air that you breathe out be stuck to you when you breathe it out?
Don, escape velocity means that if I was to throw something up and it happens to be 25,000 odd miles an hour for the Earth, that means it can of the universe.
I agree. Have we anything proven that it can even just leave the Earth?
Someone at the other side of the universe to actually follow a
period.
ball.
For me, I go with like Apollo. To me, that's like the first citation of when it happened. Although,
no, they didn't.
They weren't setting it out for that to be the study. I'm just saying that's the first thing I know of.
They didn't need escape. It's not relevant. Not relevant.
Okay, Rumpus. I'm just telling you what's relevant to me.
Well, it's not, because you're talking about Apollo. That's got nothing to do with escape velocity. The escape velocity...
I'm trying to put on record something that I know in the scientific community that essentially seems to be on record of achieving that. That's all.
Well, we know what escape velocity is because we can work it out. And from doing for instance, we...
to the moon because it holds so much gas. I understand. I mean, we know we went to the moon because we can put 10 million gallons in there, so we know we went.
I have no idea what you're talking about. I think you've got.
I'm just joking, but listen sincerely. Can I ask a serious question? When we're in space and there's no large bodies around us, and we'd have no gravity pulling us in any direction, and we breathe out a gas, would the gas stick to us?
Well, not very much. Given the fact that normally the gas would be going at 2,000 miles an hour, it would then have to exceed the escape velocity of your mass. And as your mass is so tiny, the escape velocity be, I think, something like, for instance, when they were landing that satellite, that probe onto that asteroid, and it bounced. the escape velocity for that asteroid, I think, was something like 1 mile an hour, or even half a mile an
that's
hour.
pretty cool.
You only had to be going
So it
half a
bounced
mile an hour,
off
and you would
and
escape.
go
Hold on, let me finish my answer. So you only need to get up to a speed of half a mile an hour to escape that asteroid. Now, that asteroid was the size of what, New York or something? So yes, so a molecule will be slightly affected by you, but it will be any velocity basically for a molecule will escape from you. Yes,
Okay.
so they'll all escape because the escape velocity for you as a massive body is very, 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 very small.
See, things like this are interesting. Like, there supposedly was a probe that bounced off an asteroid. Like, wouldn't it be great to have video of that? Like, actual. I mean, we all know it'd be great.
It sent pictures.
Another.
We have
Okay.
It was just a few years ago. We managed to get the pictures of where it ended up, because it bounced a couple of times and ended up in the dark hole, and we've now identified the dark hole. So we do have pictures of the asteroid.
Please stop.
It'd be cool
Please
to have
stop.
It'd be cool to have like pictures from that craft, like snapping as it approached, snapping as it bounced.
It died.
Anyway, you're
died.
right. I'm just saying it'd be great. Name of science, more evidence would be great.
I agree. It had video on it.
Okay, it'd be great if it
had video on it.
Okay.
I don't think it had video on it.
It'd be great if it did.
Rumpus, oh my goodness.
But it's great. But it would have been great if we could have spent twice as much on the mission.
You're right. $50 camera is too much to put on there. Anyway, check this out. Check this out real quick. I got another one. Can we ask you another one?
But then you need to communicate with it and have a video link. These things are expensive. They also weigh.
Okay.
For instance, the Pluto mission, they could only get there by going around the bloody Venus and Earth several times.
Okay, you're right. We have limitations of communication.
Yes,
Thanks for pointing that out. Awesome. It'd be great. I'm pointing out it'd be great if we had them. We'll have them soon, Rumpus. We'll have it soon.
Not necessarily. Depends on when we're bothered.
Well, look, Star Trek will have it soon. So check this out. Did you guys see the Dragon capsule docking? You know how when it was approaching, it did the micro adjustments, and we saw the little air boosting out, like.
I actually missed that.
Yeah, they were doing that a little bit. So I'm curious if you guys, we say sometimes that there's going to be a limitation to that, and that's why we can't just have like drones going up, exploring out there. So how much that little air bursting can do. So I was curious if we know like how much of it was needed on Apollo to make sure that they had enough air bursts to correct and not run out of air burst fuel. They'd be lost in space forever. Like, what was the chance?
On Gemini, they went through this very procedure many times to make sure they did have enough fuel. They knew what they had to allow for to be able to pick up. Because obviously on Apollo, the service module has the third stage, and then it has to go back and then dock with the lunar module, the LEM, and then pull it out of the last stage, and then off they go to the moon. So then they've got to jiggle around. But on the Gemini missions, they went through that whole procedure many, many times. And it was one of the key points of the Gemini program was to get that docking operation sorted, to do that safely and reliably.
This procedure
around the orbit of the Earth in Gemini missions. And they did that for 3 years, making sure they could do the docking maneuver that they knew they would need for Apollo. And they went through it again and again and again to make sure they would get it right. And this is what the Russians didn't do. They didn't have the equivalent of a Gemini mission. And that's why they didn't get to the moon, because they didn't practice these sorts of docking procedures for 3 years, which is what the Americans did. And it's only because they did all that testing for the docking stuff that they knew what they had to do for Apollo to make absolutely sure they were going to be able to do it.
Okay, let's get back to science. Enough of the fairy tales. So can I get my question answered?
Reality is annoying, okay?
Can I answer? It still wasn't answered. What stops the gas molecule from going up?
Gravity.
Their weight. Their weight.
Their weight.
On them. Just like a ball, when you throw up a ball.
Forget the ball. Gas molecules.
The ball is identical and analogous to a gas molecule, and just like the ball comes back to you.
Cool story.
It doesn't.
What about the thermosphere?
All the layers of gas, right?
What about the thermosphere?
What holds it?
Just like a ball.
What holds those layers of gas?
We told you a ball thrown up comes back. So do the gas molecules.
But the ball has friction, you said.
Yeah, so that's the difference. So gas molecules don't.
Elastic, meaning there was no loss in energy with those collision. So eventually, they make their way up.
They're always moving freely, right? Always moving freely in every direction.
Semi-freely. Not freely. They have weight. If
they're not bonded.
Hold on. If they have weight, how can they move freely? Don't be dumb. Come on.
Are they bonded together?
No.
No.
Then how are they staying in position in
I just
rotation
told
with
you
the
they
Earth?
run into each other.
How are they staying if they're not bonded?
They have weight.
They're not bonded, right?
There's a gravity acting on them, pulling them down, just like a ball's pulled
How
down.
do they stay shifting now, guys? Pay attention.
How do they do what?
If they're not bonded, how are they staying with the rotation of the Earth and forming
because they're
all
bounced
your
about.
all your layers of gas freely moving?
They bounce into each other.
So as the Earth rotates, the mountains on it, for instance, the gas molecules in the direction of the rotation of the Earth, and that makes them go in the direction of the rotation of the Earth. Just like a sander or something like, I don't know if you've seen a rotary sander, where if you put a sander surface on with two rollers and you spin it, you get the gas, it would eject a gas, a wind off the top of that sander in the direction of the rotation, just like the rotation of the Earth would do the same thing to the atmosphere.
But more importantly, the molecules themselves bounced into each other, and the air, when it was created, had the momentum given to them by the Earth. When they were formed, say oxygen coming off of a tree, that oxygen molecule is already going with the speed of the Earth, and even if it goes upward, it will hit other molecules that are going that same direction, and will keep it going in that same direction. Will not let it slide backward or make it go even faster.
Correct. Yeah. So, and all the molecules, once you've set up this little wind down at the bottom, it actually gradually migrates, as Anik said, through the collision for things that are above it in the same direction. So you effectively got a shear force. I don't know if you're familiar with shear forces and viscous forces, where if you slide two things and one, and you have a medium between them, they transfers the sliding force between them, and the same thing happens with a gas. So something like if you put syrup between two plates and you move one plate, the other one will move as well. Similarly, you can do the same thing will actually occur with gases.
Did you ever see my rotating candle, guys? The candle was rotating inside of a chamber and had a videotape inside of it, video camera inside of it, and it shows that the air moves with the chamber. In fact,
some will stay stasis like that until you get other shit blowing it around, and then it's not going to have
no disputing. There is convection currents. There's temperature disparity in the atmosphere. There's wind currents. There's all sorts of dynamics that goes on in the atmosphere.
There's an infinite volume.
So I'm in the middle of a fucking second. So the Earth rotates, and because of all this rotation, crazy things appear to happen, but they're all due to the fact that it's rotating at a very high rate of speed.
And they all add together. So there's this one on the equator, for instance, we've got this 1,000 miles an hour rotation of the Earth, and it bashes around the molecules at 1,000 miles an hour, and so eventually all the molecules pick up that same speed, so they move together.
Yeah, they again, until that origin is broken from the wind that is then created, or from whatever creates the wind, then we see winds happening, and so the door now.
The conservation of momentum means it can't go anywhere. Once they've got it, they can't get rid of that momentum.
Rumpus, why don't clouds have conservation of momentum?
Why do they?
Why don't they? They move
well, they
in
do.
different.
They're still. I mean, obviously, as you said, as Anik said, you get these local forces that are added to this underlying force,
which are
greater.
They're greater than the conservation of momentum of the Earth rotation.
Well, they're not. No, the clouds do not move around at the speed of 1,000 miles an hour.
Then if those forces, those alternative forces aren't greater, then the clouds would all move with conservation of momentum, correct?
What are you talking about?
So can you say that again?
Conservation of momentum with the rotation.
What do you mean they do? Conservation of momentum. You're making yourself very unclear. The clouds are up there. Let's say you have a real still day. No, like last night around in Northern California, not a breath of wind. It was really almost eerie, like we're almost inside. And the clouds above us, there were a few puffy clouds. They weren't moving either. Everybody was going 1,000 miles an hour. So momentum is conserved because you can't slow them down unless you apply a force to them. But if those clouds were to be towed, let's see, tie our lasso around them and tow those clouds to the equator, conservation momentum says that we would have to speed up if we're going to go down to the equator and match that tangential velocity of the surface. which we can't do if we put a friggin' rocket in front of that cloud. So what happens to the cloud? It'll lag behind. The Earth will appear to rotate underneath it. That's what the
I want to see that happen to a helicopter. They say it can. But look, guys, I don't want to change the subject, Xanax, but I'm blessed to have you.
Don, you're flying the helicopter south. Same thing. You have the momentum. To conserve momentum, the tangential velocity of the surface less than you are in Northern California. So you either better speed up or you're going to be left behind by the Earth.
Right. So in theory, you could stop and then video record the Earth turning under you. But again, please, if you could bless me, I got you and Rumpus here. I don't totally want to change the subject. I've been dying to ask you guys something. Maybe it'd be good since y'all are recording. It might be something new. And I don't have that much time left. I got to go here in a couple minutes.
Okay.
Do you guys understand the atmospheric electricity very well?
Are you talking potential in the atmosphere that increases with height? Is that what you're talking about?
Yeah, the potential gradient. Yep, PG.
Yes, that's what you're talking about. Right. Okay.
Yeah. I'm not trying to trap, dude. I'll just say, I don't know anything about it, and I'm trying to get there and learn more. Right.
If you want to know about that, if you could go online, I think I've got a link to a Richard Feynman lecture that he talks about this very thing, the atmospheric potential, and he even draws a little diagram of a little man and how the potential goes over his head because you as a person all have the same potential. So when you go and move into an area, I think it's every meter increases by 100 volts or something.
Right. So can we talk about that? Do you understand the numbers pretty well? Are you familiar with them? I've seen the diagrams. I've seen some more complex diagrams that have like multiple variables involved.
I tell you what. I think I've got the link.
Guys, sorry, I got to interrupt first. Hey, Righteous, if you can hear me, Red Man's trying to get into this room, and for some reason I can't move him in here. So if you could do that, that'd be awesome. He's in biblical below us. Sorry, guys. Go ahead.
All right.
Cool. So, Rumpus, where did they say that that's coming from? Is it from? And I don't want to argue if it would be possible or not. I'm just saying, where did they say it's coming?
That is weird.
I don't know the answer to that off the top of my head, actually.
Wouldn't friction of the particles cause?
When you rub things together, you have a loss of electrons. Like when you rub a balloon, you rub some of the electrons off, and then you generate a potential. I don't think it's that. I must admit, I'm not quite sure.
Because there'd be more. There's less of high. They're rubbing more.
Hold on, let me just try and get this. I've got it somewhere here. Let me see if you can.
I have a couple links.
Yeah, but I've got the Feynman thing, and he goes into this. He spends a whole lecture. Well, not a whole lecture, but half a lecture going. And if I can get the link to you, I will see if I can. Here we go. Electricity in the atmosphere. I've got the link here. Let me just get it for you.
It's some.
Yeah, we're in this recording one or something.
Yeah, no, it seems like things changed. Like you guys were in the room above before.
Yeah, and I don't know who moved us or if they just changed the room or. But I'm noticing that when I
don't know. We were in the after show. Now we're below.
Yeah, you're.
Didn't you do it, Righteous? You changed the name because Kimo recorded us.
Does changing the name automatically change the order?
It must.
I'm not sure about that, but whatever.
So.
Alright, wait a second. I can see the recording and it keeps changing. What the? That is weird.
It might just be a Discord issue.
People can't apparently enter this room. That's why the room was shrinking, maybe.
Right, because it's over full right now. And what's weird is I can move people out of the room right now if I wanted to, but anybody that was outside of the room, I don't even have to move them.
Yeah, even me. I'm like, I think Fujix figured it out.
Chat thing, Righteous? So
Can I try to move me?
Can people see my screen grab here? There's the Feynman lecture with the little diagram here.
Yeah,
let's see if we can figure out where they say it's coming from.
Okay, well, okay. If that's your question, but I'm just showing you here the Feynman lecture. the Feynman lecture on this subject, the electrical potential gradient of the atom, and I can't remember what the cause of this is, but it exists. And I hopefully, I'm not going to. It's too late now to start telling you about the difference between potential and the difference between voltage and the charge.
Yeah. I just wanted to see if we could see, is it like a hard lock on the origin, or if it's still flexible. I find it interesting that it seems to start at sea level.
Well,
the conclusion. Is the conclusion flexible, or is it a hard, nobody's arguing with the conclusion?
What conclusion? What are you saying?
The conclusion of the origin, of the cause of this.
All right, what the origin is, right. I don't know. Where is it?
See, it's interesting, right? Because, if it's starting at sea level, what's under sea level? What's happening?
See, well, at the ground is regarded as an equipotential. That's why we have an Earth. So that's 0 volt. Just like when you earth something, that's at 0 volts. There's nothing under the water. The water would count as being ground as well. That would be at 0 volts as well. The only reason you've got a voltage gradient here is because it doesn't conduct electricity. You can only have a gradient in something that doesn't conduct electricity. Air is not conductive, and that's why you can have a potential across it. If the air was solid metal, there would be no potential gradient, but because it's not a conductor, that's why a potential across it.
Then why you have a potential?
Why? I don't actually happen to remember now, and I'm trying to read here.
Clouds.
Well, no, this is nothing to do with clouds. This is actually.
I don't think so. No, air is not conductive. Why would you have a electric charge in it?
Sorry, what's the question again? Why do you have electric charge? Well, obviously you have electricity. You mean lightning? Is that what you mean?
Yes.
So are you talking about lightning, or are you saying, well, how can clouds? I mean, atoms are made up of positive and negative things. So when they separate the two, it happens. The cause of lightning, for instance, is that ice circulates in the cloud, and just like a balloon rubbing together, causes electrons to be removed from the ice, and that causes a potential difference. And then eventually, when it gets the voltage difference becomes sufficiently large, you then get a lightning to discharge that potential difference. But it's
actually, then the layers of charge are built. I don't know exactly, but I think I have some video here.
Sorry, I'm not quite sure. Are you saying? Are you disputing there's a potential in the atmosphere, or are you saying how does?
No, after the cloud, when the clouds start to develop the electric charge, the layers of.
So you're saying this is entirely. Are you trying to say then that this potential in the atmosphere is due to clouds?
Oh my goodness!
Is that what you're trying to say?
Yes.
Really is. You are just
what, the formation of clouds? I mean, the fact they rise up. Is that what you're? Why is TV on? Is that?
No, I think it's Paul. I think you got a Paul or you got an open mic.
Right. So that this potential was created because of convection and the creation of cloud in the atmosphere. Is that your claim? Because clouds are not. I don't think clouds in themselves are necessarily charged in any way. It's only after it's only in a thunderstorm cloud, I think, where they have this thing where they suddenly acquire charge. I don't think clouds do not have a particular charge, as I recall. If that's what you're claiming.
Right. The charge is built at certain conditions.
So what are you saying is building them then?
Because what you described, they get the ice particle.
Okay, yeah, right. But we're talking here. We're not talking about the clouds. We're talking about why is there an atmospheric potential independent of clouds?
Is there?
So yes, that's what this diagram I'm showing here. Richard Feynman's leaving a lecture on it. Oh my God.
Then just post the lecture.
I put the bloody link in there, you twat. Jesus Christ! I'm sharing it. I posted it. What more can I do? I put it in again.
Easy, Rumpus.
Jesus
easy.
Christ.
So Rumpus,
Easy,
Rumpus, can I summarize a little bit of what you were kind of hypothesizing
Anything
so far?
to save me, yes. Go ahead.
So it's so maybe it's like coming from somewhere underneath, but because there's ground, it's just going through because it's whatever. It's just going through the ground, then it's released, and then it's starting where you're saying that it's the air. Is that kind of what your summary was? Like, we're thinking maybe is why it starts at ground level? Testing.
Right. Okay, I think it might be something to do with cosmic rays. This is what might be the cause. The fact that cosmic rays are hitting the top of the atmosphere, and then gradually that gives a potential difference between the top of the atmosphere, or wherever the cosmic rays are bashing down to the bottom. So that seems to be the cause, I think. And that can even cause current.
Yeah, I'm totally not trying to do any dude. I just know the scratch of the surface of some of these things. I know we also have the magnetic field going on. I didn't know they're tied together at all. But like, that's interesting, the cosmic rays. I mean, it's just cool to think about, like, hey, you're like, wow, I don't even know that origin. Like, maybe that comes into play in some of these things we're asking the questions to. How is there a grade? I know it's radical, but it's another thing. The cosmic rays are causing an effect on our atmosphere.
And in this lecture, he interestingly observes that the peak value of this current that goes from the Earth's surface to the sky, or whatever, vice versa, it always has its peak value when the London 7 p.m. I don't quite know why that.
At what time it has it?
Yes, it changes obviously during the day, presumably, which is a bit odd, obviously, given that I presume it's something to do with the fact there's more, I don't know, ocean or something, orientation of more ocean, the fact that Earth is not symmetric or something. I'll have to read it more, but yes, I'm getting a bit tired here. So, but anyway,
okay, look into it, man. I think it's worth thinking about.
Well, I'll give you a link to this lecture, and it talks about how this is formed, and then goes on how thunderstorms work, which is obviously the thing I was talking about, where the particular voltages and potentials inside a cloud are caused by the flow of ice and things, which is a separate thing from the atmospheric potential. There's the potential in a cloud, which is separate from the atmospheric potential, and he goes into that as well. So if you want to understand it, there's a lot of explanation in this lecture that I've just linked to.
It's also, when you're doing your research, look into sprites, because the electrical charge seem to come from the ground up with lightning, and then from the container down, or the sky down, with sprites.
Yeah,
they seem to be electrical charge too.
Indeed. Someone's got their bloody mic open again. Yes, indeed. The lightning, the way it works is it breaks down from the top, and then it gets to so far down close to the ground, and then in fact there's a certain name for the charge actually comes from the ground up to meet it. But the sprites indeed are something else. Sprites are these very peculiar things where the upper atmosphere, they didn't realize they existed until about 20 or 30 years ago or something, where these things shoot up from the upper atmosphere upwards.
Yeah, it's brand new.
Yeah, so that's a different thing, and of course we know there's no container, we know there's no dome, because there's no evidence for it, and of course we don't need it.
Yeah, we don't know that yet.
We don't see a gradient
ending. There's not a single piece of evidence. We know there's not a single
pot ripper anomaly.
The fact believing that we've escaped was very telling. But Rumpus, before you get too tired, what was that force that you gave that would make clouds go from east to west?
Drag. He was talking about drag. The change in tangential.
You're talking about conservation of momentum. The fact that they follow the Earth rotates, and it drags, by fluid mechanics, it drags the atmosphere with it.
Yeah, but sometimes we have clouds that go from east to west instead of west to east.
Relative.
What force would cause that?
Relative to the surface of the Earth, there's winds. I mean, we know that we can generate winds and convection currents, and that's added to the rotation. There's still, if they were to stop, they'd be then moving relative to the surface at 1,000 miles an hour at the equator. But yes, little local effects are added on to. So if you have a convection current that happens to go in a particular direction, or as a result of Coriolis forces, you tend to get cyclones or something, and you get a non-symmetrical movement of air, then yes, it will cause local winds, which will be added on to the
convection currents and wind.
Yeah, so we have winds on and that's added on to the velocity they have, so 1,000 miles an hour, and you can still have, just like, for instance, if I was to take a big tank of water and put it in a truck, and I was going along at 100 miles an hour on a motorway, that thing, the water in there would be doing 100 miles an hour. but I could still wiggle and paddle around in that bath or have movements in there that are just added onto. And so the velocity of any particular molecule would be the 100 miles an hour plus whatever the local motion is, and exactly the same is true in the atmosphere. So the equator, if it's doing 1,000 miles an hour, it's got a little convection current. Yes, you can still have a 20 mile an hour, 30 mile an hour wind relative to that.
So it's dynamic winds and change in tangential velocity is causing the hurricane, not the Coriolis. Well, whatever.
So Rumpus, so all the new gas that's hang on, Rumpus, before you go. So all the new gas that's being produced that rises up, how long does it take to become the same speed of the rotation? Like, you know, to gather that speed and become fluid.
The speed. Remember, we've been around 4.5 billion years. The Earth's been around, and it has an atmosphere.
No.
Boy, it's just gotta keep getting deep.
So it's picked up. So it's. Well, what do you mean new gas? Gas
is being produced every day. How long does it take?
Well, very small. Not in comparison to the body of gas that already exists. It's a very small proportion.
Okay, that very small portion. How long does it take to
It was in motion already.
Yeah, exactly. Imagine it's being emitted by a volcano. The volcano at the equator is doing 1,000 miles an hour. So when it leaves the top of the volcano, it's already doing 1,000 miles an hour already. So that's where it's got its velocity from the fact it started off with it. And it conserves that momentum, and it doesn't suddenly stop because there's nothing to stop it.
Can you repeat that? No, can you repeat that scientifically in a test?
Well, we know that the Earth's rotating 1,000 miles an hour at the equator.
No. Don't tell me. Repeat it, scientifically. Repeat that test.
Repeat it scientifically. Do you want to... We know,
from
science...
Rumpus, why do you do that? Why do you do this?
Why do I do what?
Tell it's not fair to the argument to say we know.
We do know.
It's so not fair.
Unless you're a science denier, the body of human knowledge and science says that the Earth at the equator is rotating 1,000 miles an hour. That's what the body of science. That's what our body of science, our body of knowledge, and anybody studies this and does their professional, and all the institutions around the world that worry about these things come to know the same thing, that the Earth's rotating 1,000 miles an hour. So if anything like a volcano emits some gas, it will start off rotating at 1,000 miles an hour.
Right, but you're disrespecting his argument, man.
Okay, Rumpus, can the body of science repeat that?
Bob did.
Oh, here's cheeky.
Bob did.
Yeah, Bob did indeed.
Hello, can we repeat that test? Simple question.
Only cost $20,000 if.
Can we repeat the gyroscope?
Listen. You Rumpus, you've given the sand belt example. I think that's how Rumpus says it is repeatable. So maybe we should dissect that, because Rumpus, you definitely have
gives an example of how. Yeah, the sand belt gives an example of how gas can be speeded up by being in contact at a surface that's rough and speeding it up.
Am I incorrect in understanding that you said in these demonstrations it also shows it start to come into a stasis of rotation?
Never used the word stasis, so I don't know. What do you mean?
Well, we talked about it, and then we said that it'll spiral, but then we said, it's gonna drag on the container, and then I'm like, okay, so can we have a stasis?
So I think what you're talking about is the fact that does the upper atmosphere move at the same speed as the lower atmosphere? And the answer is it doesn't. So, for instance, the Earth is rotating. Let's go with the equator again, because that's the interesting bit. Going at 1,000 miles an hour. So any gas that's coming off a volcano, for instance, we were talking about, comes out going round at 1,000 miles an hour. But if it goes up and up and up and up and up and up, it's still doing 1,000 miles an hour. It's conserving its momentum. It's still going 1,000 miles an hour. But of course, like a tire or a wheel.
Okay, so circumferential difference will make this drag. We got it. Okay.
Correct. So in other words, it'll fall behind. So as the atmosphere goes up, but it's only a difference of about 20 miles an hour. So actually, the difference between the surface of the Earth and the upper part of, say, the Kármán line is only about, I think, 20 or 30 miles an hour, which actually is insignificant in comparison to local winds. So actually, it doesn't really have any net effect, because the winds are much more important and have a much bigger effect on the difference of velocity, just like a wheel at the midpoint of a wheel and the top of the wheel are going at different. But of course, for the Earth, if you want to do a comparison with the Earth, it's like the tire tread, the top of the tire and the tread above it is the comparable with the atmosphere's height. It's so small that the difference in velocity is so tiny, but it is. But winds are
okay. So instead of using that though, because he's asked for the demo, so instead of people are going to argue that we're making a a presumption if we use the Earth as the demo.
Well, we have there are things that go up there that measure the speed of the atmosphere. We've got I've got a paper somewhere that shows the speed of the upper atmosphere, the various speeds at the atmosphere at different heights. I mean,
so how would we answer Paul's query? It was Paul, right? He said, "Well, can science demonstrate the air coming out of the volcano and staying above it? You know, can we demonstrate that in science without the Earth? Can we do it without the Earth?"
Light the fire. Come on, light the fire. You see the smoke goes
we're
up.
still using the Earth there.
It goes up.
Oh my gosh.
When the volcano, what use? Not Earth.
The point is, we're talking about something having the momentum, keeping that.
So we know that happens. So you accept that's a fundamental principle of physics that momentum is conserved. We know that happens.
Sure.
So something. So for instance, if you're in a train, for instance.
Yeah, but we know what happens, but that doesn't mean that is what's happening. We also know that when something's still, it stays still.
But yeah, so hold on.
Right, there you go. How can we prove it's not just staying still, Rumpus? There we go.
If you're in a train that's doing 100 miles an hour. Yeah, so now we're in a train. Yeah, we're now in a train. So I'm demonstrating a principle here that is universal. If you're in a train that's doing 100 miles an hour going in a straight line, you pour yourself a cup of tea. The tea, as it leaves the spout, is still doing 100 miles an hour. That's why it then goes into the cup.
Yeah, and that would happen if we were still also.
Yeah, I was just going to say, hold on. Let's park the train.
That's why.
Pour the same cup
you
of tea.
cannot distinguish between moving at a constant velocity and being still. There is no different.
But we know the Earth is moving.
Can I just finish the sentence? So there's no physics test in physics that you can do that will distinguish between traveling 1 million miles an hour in a straight line without being able to look out the window and outside an outside reference point. There's no experiment you can do with balls or mechanics or anything like that will work out that you're doing 1 million miles an hour if you're going on a straight line and not changing velocity.
So what's the outside reference point for the Earth?
Well, that's why we know we're moving, because if you look out the window of a train, you can see, in fact, you're going very quickly relative to the tracks.
So where's the window of the Earth?
I'm just about to say, you just interrupted my bloody
answer. It's called sky.
Yeah, so when we look out there, we can see indeed the space is rotating, but we also know that we are rotating, and it's not doing that. For a start, if Neptune were going at the speed of light, but we can see Doppler effects of the stars, so we know that we are moving and not the stars. So, and there are various other things like, the focal pendulum, the Bob's test with a gyroscope also tells us we're rotating. The fact that
2020 and we're still
things that the Coriolis effect tells us we're rotating, and the fact that things weigh at different mass, different weights, or different latitudes also tells us the fact that when you drop something in a vacuum chamber, it doesn't land exactly underneath it. It's affected by the rotation of. So we've got about 10 different experiments we can do and conduct. So hold on, let me finish one second. Nearly there, 5 seconds.
God,
we've got about 10 different ways of very easily verifying that we are.
And you just made 10 points, but we're interrupting.
I'll finish. Carry on. Go ahead.
Okay. Except, so you say, and drop a different direction, not a different direction, but they
don't fall at the bottom. Yeah, they don't fall directly underneath them. Yeah.
Right in the vacuum, except for that people. There's these guys on YouTube and on Facebook that drop shit on stuff from a high tower all the time, and it drops straight down.
No, it doesn't. No, it doesn't. No, it doesn't.
It does actually.
No, it doesn't.
Actually, it does.
No, it doesn't.
No, you haven't got the exact measurements there, gods.
No, they don't. That's actually
not true. You're talking about such a small deviation. You can't measure it from 20 feet.
Put in a vacuum chamber.
Vacuum chamber. You got distances. You got to control your experiment. It's called the scientific method. You should be familiar with it.
You need that we're measuring.
You got to go.
How big's the vacuum chamber that we're measuring this deviation?
100 meters. 100 meters.
100-meter vacuum chamber?
Yes, they exist in Germany. There's a special vacuum chamber that exists to do this very. About 3 inches for 100 meters.
3 inches for 100 meters?
3 inches for 100 meters, yes.
Do you think yelling is going to make your point
Well, because I've been trying to get this point, and all you've done is interrupt. I've been trying to...
What are you talking interrupt? You said you were done talking, and I'm trying to make a point now, and you fucking went on for
and
hours
I was trying to explain to you. You said, well, how does that happen? And we've got videos of this. But we're trying to explain to you that's not scientific. You need scientific conditions where you control all your variables. So you've got to do it in a vacuum to measure it properly. You can't just get up the top of the house and then drop it down and say, oh, look, then it went approximately within an inch where I dropped it.
Okay, shut up for a second. So they have this tower, and even with the wind and everything else, the atmosphere, it's still
vacuum tower.
It's still dropped.
No, it doesn't.
Yeah, it doesn't deviate. The objects they drop don't deviate.
No.
How do you know?
How do I know? You can go watch the videos, dude.
Yes, but you can't watch the difference.
Okay, do you know how they
Tell
do
me,
it?
tell me.
Listen,
Can you tell? I'm asking you a question. Can you tell me? No, you talk non-stop if you didn't.
I talk non-stop. I haven't said a word for like hours.
Can you tell me a sharp knife from not a sharp knife by looking at it?
What the fuck are you talking? Who's talking about knives?
Can you tell by looking at something?
Anyhow, so they have this tall tower. They have this tall tower, and let's say they want to drop a bowling. So they hang the bowling ball off the top, and then they pull it up, and wherever it was hanging from, like they put the object that they want to hit the bowling ball underneath it hanging. Then they pull the bowling ball to the top, and then they drop it, and it happens to hit the fucking target. Wow.
Well, because they know where to put the tape.
Could they measure a couple of inches off? I don't believe it. How do they know?
They don't measure. I just told you how they do it.
How?
They hang it.
Right.
Then they pull it up from that
vertically above it? How do you know what the vertical position? When they dropped it, they had to position it somewhere away from the building. How far did they do that?
I just told you if you would listen. They hang the object they want to drop from the tower over top. On the just off the ground, over top of where it's gonna hit. And
how?
You know what I mean? They just use a winch,
pick
it straight up from that point.
Know what's vertically underneath where they're dropping from?
I just fucking told you.
No, you didn't. You did
they
not
pick
explain.
It straight up with a winch, and then they release it, and it falls right from the point that they picked it up from.
Straight up with a winch, did you say?
Yeah.
Is that what you said? I didn't hear the word winch, right?
Well, that's because you're too busy yelling.
No, because you're not articulating it carefully enough. Right. The point is,
it has nothing to do with you yelling. You're right.
Right. So how do they? Yeah, but the point is that when this is done scientifically and accurately, you get the deviation. About the same as many YouTubers. Yeah, so you're just laughing at science. Yeah, you're just laughing at science. You're laughing at science. You're laughing at experiments. You're laughing at professionals.
That's why
you're laughing at professionals who do the job with an institution that's designed to do this very experiment. And you're comparing with some of the YouTube video. I mean, you're an idiot.
They drop shit every day, dude. They drop shit every day, and it always hits the target.
Who are you talking about now?
Always hits the target.
These people that do it, that's what their niche is.
Nowhere, no one measures.
What?
No one measure where it hits, where it was before.
Yeah, that's how they do it.
I know they. Show me.
Cheeky, have you seen these experiments?
Come
these
on,
guys dropping it?
Show me. I saw them dropping a lot of stuff.
Oh, you saw it?
So then you should know they hang it over the.
Let's see it.
To drop.
No, you're just saying they didn't measure. You've never seen it.
Yes, I saw them dropping the big ball. You saw it.
The point is, when you do it properly, scientifically, measurably, verifiably.
Just because you put science in front of it doesn't mean it's proper or not proper.
So these people have a vacuum chamber, and
These people are doing it all the time.
Oh my god! What do you mean? So what? Then
it's
it's subject to winds when you're talking about. It's subject to all sorts of other variables. Eliminated by doing it in a vacuum chamber. You cannot dispute this. People who are doing this professionally, and you're comparing it with some of the YouTube video with a wind affecting these things.
Then it still drops straight down, dude. They still
I don't believe they've measured.
Did you measure, Goat Scalpel?
Did
you measure it? Let me see where it was, where it landed. Your eyes don't mean no. Your eyes don't mean anything. What they hit?
You said you've seen
a big table.
What are you
a
talking
trampoline.
about?
What do they hit?
They CGI'd it or what?
No.
What
do they hit? They hit the pinhead. What do they hit?
Oh, they hit all sorts of shit.
Yeah. Trampoline, big deal.
Sometimes.
And not at the center.
Sometimes it's smaller shit.
Yeah, I saw. They hit the trampoline, not at the center.
Not the only thing.
Not at the center.
That's just
show me. I ask you, show me, and you keep talking, not show.
Whatever. I don't know what to tell you. It's like,
yeah, I saw it. I saw. Post the video. Post the video.
That is one of them, but it's
Well,
not
I
just
cannot believe
trampoline.
you really think that someone doing something in the open air it compares with a vacuum chamber 100 meters high, where these have professional measurement, professionally calibrated instruments to measure this effect, and you think those two things are comparable. I mean, if you live in that world, then you're a science denier. You don't understand experiment. You don't understand measuring things. You have no appreciation of science at all if you think that's the case. Yeah, you're science denier. If you think
Nothing like
things are equivalent,
poisoning the well,
if you think those two things are equivalent, then you are a science denier. You have no the levels that people go to measure these effects so that they are consistent and verifiable. If you think those two things are equivalent, a YouTube chappie chopping a thing in the wind is somehow comparable to a vacuum chamber where they've eliminated all the other variables, then, I mean, there's no point in reason. You can't reason. There's no point in trying to explain anything to you if you think those things are equivalent.
Okay.
You're just a science denier.
What's the name of this?
You have no value of science at all.
Yeah, I know. What's the name of this 100-meter vacuum chamber?
It's in Bremen. I think I'll go and get a link for it.
Sure.
It's in Germany. I mean, there are others. I think there's an American one as well, but the one I happen to always remember is the German one. But I'll go and see if I'll get a link for it. And they're always dropping things because that means you can emulate weightlessness in the 10 seconds or so that it takes to drop. You effectively have a weightless environment. So they do lots of things.
What the fuck are you talking about? A weightless environment?
Yes, things in free fall.
How does evacuating a chamber make you weightless?
Listen. It's the falling in free fall. Just like if you were to drop in a chamber, you would not feel your own weight. The only reason you feel your own weight is because your legs are pressing on something that's pushing back up. If you were to drop you in the sky, even if there was a vacuum, the only reason you slow down is because if I were to drop you in a vacuum, you would not have any weight. You would not feel the bottom of your body, and the top of your body.
You would not have any weight.
The acceleration you would effectively be weightless. If you were in free fall, you are effectively weightless.
How do you fall if you have no weight?
You would not feel any pressure difference between your feet and your head. Your feet would not be supporting you anymore, and all of the atoms in your
if you're weightless, Rumpus, therefore, there's float.
You would feel weight. I'm talking about how you would feel. You would feel weightless, and similarly, things that are dropped in a vacuum chamber effectively cease to have weight.
If you were weightless, you would float.
No, mate, you would.
Yes, you would.
You can. No.
Yes. You guys are talking about feeling compared to what actually weightless would.
Okay,
you would feel weightless fine, but you're not weightless.
Do you know what a parabolic flight is?
Parabolic flight. Yeah, you know what a parabolic flight is.
Yeah, in a parabolic flight, are you floating or are you falling? Are you floating in a parabolic flight?
No, you're not floating.
Okay, but you still feel weightless in a parabolic flight, aren't you?
And things like the density
feel, but you're not weightless.
No, you're tricked. You feel like you're falling in a parabolic flight.
Hold on, Scalpel. Have you seen the comic comment? Have you seen density
tower? No, you do feel like you're falling.
Yeah. Have you seen the density tower video where people get veracity density of liquids in a density tower, bit like the one that Anthony Riley used to go on about all the time, where you've got the dense liquid at the bottom. Well, hold on, let me nearly there.
Yeah, where's your link for the vacuum?
Nearly there. So that density tower, you've got the most dense liquid, the oil at the bottom or level, all at the top on the milk,
whatever.
All the other things. Right, so they separate to the deck. Right, you're familiar with the density tower. Great. So when you take that and you drop that, they cease to have layers anymore because they're effectively weightless. You can emulate weightless. You can emulate weightless conditions by being in. Yes, you can. You can emulate, and that's. I've just given you a link. I've just given you a link to it in the text.
Don't interrupt him. It's so irritating to listen. Let him finish his thing before.
So I've given you a link to the tower in which, and that's what they use it for, because they can get atoms and things to behave as though there's no gravity on them, and that's why they do experiments with it. And I've given you a link there to the tower in Bremen. Give it the tower in Bremen, which is a vacuum chamber in which they can do these experiments, in which they can measure the deviation.
Where did you put it?
I put it in the text. Oh my god!
Scalpel, what are you on? Like 4 cylinders today? What's going on?
Oh no, I was in the wrong. Actually,
Rumpus, calm down a little bit, man. Calm
Holy
down.
fuck, you guys need
No,
to
but
relax.
Scalpel, you're being irritating. Stop it.
Shut the fuck up. You're always irritating. At least for me, it's only today.
Well, I'm always irritating because I don't agree with you.
Come on, Zanuck. You wasn't doing that earlier. What'd you go do something?
Yes, you said yes.
Well, no, I mean, he's just, I want to hear Rumpus's thing, and I just.
No, you've heard Rumpus for hours. Just calm down. We're all being civil. We're all being civil.
I'm shutting up now, so you got your wish.
But I mean, you gotta like let people talk and just don't run over people.
What are you talking about? Rumpus has been talking like 90 to nothing.
Well, you're asking him the questions. He responds to the
Oh
questions.
my god, everybody get over it. Vaughn, fuck.
No, it doesn't. No, I get it. You know,
God, let's talk
so
about
irritating
who
to listen
talked for
to.
how long and who's annoying and everything for the next 20 minutes.
Just
Just
irritating
get
to listen
over it.
to.
Fuck's sake.
It's hard to listen
12?
to.
Are you fucking 12?
All right, gotcha. That's why I gave the elevator example. When you have the elevator going 1,000 miles an hour upward, and suddenly the force is cut. What do you feel? Weightless, right?
Yeah, but you don't feel weightless. It's an illusion that you feel weightless. You feel like you're falling.
You have to
after you start.
Yeah, it's the same feeling.
Is there any difference between falling and floating?
Well, that depends on if you're looking or not.
It depends. No, if seal.
No, Zanuck, your body. Listen, when you say feel, we're going to be specific here, Zanuck. It will feel different if you're allowing your brain to trick you.
Listen. So you have a elevator. It's going 1,000 miles an hour upward. It's a real long, tall building, right? But that cable breaks. We went over this before. As soon as that cable breaks, you're still going close to 1,000 miles an hour.
Yeah, in that case, it feels like you're rising up.
As soon as that cable breaks, and this elevator has no windows, you feel like you're floating.
Or you feel like you're rising up.
No, you feel like you're floating. Like you're suddenly weightless.
You don't say no to me. You agree. What we're saying are both acceptable answers, Zanuck.
No, you don't feel like you're rising.
Yes, because that's what rising. Zanuck,
hold on.
Why rising?
You're literally rising, and that's what you're feeling.
Oh, that's what it is. Let me address
that. Don't. Why rising? Why?
Because that's what's happening.
Why? Let me explain.
You'll feel nothing, which is what rising feels like.
What the fuck? So as soon as that cable is broken, you are weightless, and you're still going upward. You say you feel it. Okay, let's just address that in a second.
I didn't say I felt it.
You feel like you said you still feel like you're going up.
No, I said you feel the feeling of what it feels like to be rising, not accelerating.
Okay, stop. Fine. So you think you're rising. Cable breaks. You think you're feeling what it feels like to rise. Now we're rising up, and it's slowing down 1,000 miles an hour, 900 miles an hour, 6. It stops 0 and it starts to accelerate downward.
My rhetoric will be the same in that direction.
It's done. You gotta focus.
To the end.
You gotta focus.
So slow.
5 seconds. Seriously. It starts accelerating 5, 10, 100, 200. Now it's going 200, 300 miles an hour downward. Now, during that transition of going upward and then coming downward, did you feel any difference?
Yes, the acceleration change.
That's where you're wrong. You don't feel anything.
You don't feel.
No,
you don't. You don't.
Your mind.
You will feel. Hold on. Let me clarify that. Hold on. Are you saying through the apex? You're telling me through the apex you don't feel nothing? You're full of shit.
Yes.
Guys, stop yelling. I want to read what did anybody else read what fucking Rumpus posted to me?
No.
This is fucking okay. So it says Tom Scott recently visited the Bremen Drop Tower at the University of Bremen or whatever in Germany. It's a 100-meter tall vacuum chamber that lets scientists test zero gravity experiments on Earth. How does a fucking vacuum chamber create a zero gravity situation?
When you drop something, it's zero gravity.
Why does it fall?
Right.
You drop it.
Why does it
this
fall?
is why they disrespect. I totally agree with you, God Scalpel. In the vomit comet experiments of buoyancy, they misinterpret this conclusion. They don't accept that it's actually falling through the reference
Calm down.
frame. They won't fucking.
So yeah,
so annoying.
If it's 0 G, why does it fall?
Gravity? A vacuum chamber takes away gravity.
I just got done telling you about the elevator. It's the same thing.
I give a fuck about an elevator right now.
That's a misunderstanding from you, dude.
You drop the elevator.
Of me?
You drop the elevator. And
well, that's what the article says.
It's stimulating 0G. Why are you talking over me, Scalpel?
What you don't understand?
It says the sign. It's let the
sign. Scalpel, they don't say to make it float. They don't say that, but they do want to.
You drop an object. Everything inside the object is 0G.
No.
Zero gravity experiment says. Scientists test.
Everything inside the object is 0G.
No, it's relative 0G. It's not actual 0G. No,
it's the relative.
You can measure it.
Wait, hold on.
This is where the fucking misunderstanding comes in right here.
Yes, then let me,
it's 0G.
Then let me turn. Why do you think Einstein say no force is acting on him?
Because he's a crackpot?
No. Because there's no force acting on him. He doesn't feel any force.
Prove it.
Prove. Go jump from a building. I'll prove it to you.
So you're telling me that a force is a feeling then? If you don't feel gravity, it's not there.
But this shit is so stupid.
If you don't feel a force pushing you or pulling you or something, there is no force.
You ballers don't even realize where the clarification should be happening here. It's so ridiculous.
Well, I don't feel gravity, so therefore it doesn't exist for me.
No, listen. If you stand on the ground, you experience an acceleration of 9 seconds squared.
No, I'm not accelerating. I don't experience
Yeah, of course, you don't accelerate, but the acceleration is because you weigh something. Okay, that's the weight. When you go, let's say, you're not going anywhere. That's why you weigh something. Okay, it's pulling you to the ground.
You gotta
the acceleration still exists.
One
sec. Okay.
So it's always there.
Right now you have. Yeah, it's always there.
Even
right now, it's always
in the tube. Even when it's in the vomit comment.
Yes. Wait. Just wait. Okay, let me explain this. Let me explain this to you. Okay.
Y'all sound so desperate.
No, if you don't listen, you will never learn.
Something. When something is falling, okay? When something is falling, doesn't matter. Like, let's say you're on a parabolic flight. The plane accelerates towards the ground at 9.8 meters per second, which cancels out the gravitational acceleration that you experience toward the ground, which makes you...
No, that's the false fucking interpret. It doesn't cancel out. It only fucking
zero at this point.
No. No. The other stuff inside is still falling. It wasn't canceled out. It just gives you the appearance in the reference frame that it's not moving inside that container. But that force is still there.
Yes, and in that case, you're weightless.
That's ignored in the conclusions of these experiments, man. Think about it.
You don't understand. You gotta think. You gotta open your mind.
You don't understand fallacy again.
Yep, you don't understand. I'm telling you, you don't understand.
Listen to Rusty explain it. I gave you the elevator example. Now listen to the parabolic flight example. They're very simple.
Okay, everybody stop yelling. Everybody try and let the other person talk. If it's possible.
Yeah, don't fight against someone who tell you something. Try to learn something.
You've got to be like Psych.
Yeah.
Gotta be like Psych.
Anyhow, you're still falling, and the plane's still falling, and a vacuum doesn't take away
spinners
on the heliocentric model. if something's falling, how can it be weight?
It's not falling.
But it is. It's just relatively not.
Wait a minute.
It's floating.
It still has mass. It still has weight, even though it's falling. It still has weight.
No, it doesn't.
It says right here, let scientists test zero
It doesn't have weight, Paul. Wait, hold on.
Ballers are so confused. You guys are so confused.
People make incorrect statements. I like to jump in. It does not have weight when it's falling. It would only have weight if it wasn't falling.
It still has mass then.
That is ridiculous. It does when it's falling. If you set a scale up under that shit, it wouldn't have weight.
Yeah, you don't have weight when you're falling.
If you put a scale up under some shit, just because it's falling, it's not going to measure on the scale anymore.
Why? Exactly. What will it press against?
What? The scale!
What will it
You
press
holding the
again?
scale. You holding the scale.
And how much? How do I press on it?
Oh
Yeah,
my God.
let's
No,
see when
if you're
someone is
saying if you're
skydiving.
falling and the scale is falling, it doesn't have weight.
What's the
That's what you're going.
calculation for
Listen,
weight?
you're on a scale on the elevator, and you're going up 1,000 miles an hour. You're weighing, and you're not accelerating, so you weigh your weight.
The
You have to say,
stupidest semantics. Waste
stop
of time
talking.
bullshit.
You're going up 1,000 miles an hour, but you're not. Your weight is your weight. Let's call it 100 kilograms, okay? 100 kilogram force. Now, as soon as that cable breaks, the weight that you see on the scale is 0. And you're continuing to go up, by the way, and you hit the apex, you're still 0, and now you start accelerating downward. You're
And
still
now once you're down, you got the weight again, right?
everywhere.
Going...
As long as you're falling or not connected to a force, you have 0 weight.
I'd like to make a statement, Zanuck. Whatever you did when you went on break, you need to get your money back, sir. You're completely two different people.
So what's the weight of the air in the middle of the container that's accelerating in all directions? What's the weight of the air?
Not all directions. Not all directions.
There's probably a confusion here
Gas
beyond
gas
mass and
expands in
weight.
all
It
directions.
doesn't accelerate in all directions, though.
How does
Paul, you're
make
so
a
confused.
zero
Wow.
gravity situation?
I just
Listen,
gave you a great example. Until you can wrap your hands around the elevator that has the cable cut,
I didn't.
and you
I
will not
don't
understand.
recall
Rumpus said to press on
elevator
a
in
You
my
got to keep
question.
on running over me, don't you? You got to keep on talking
Yeah,
over me.
because I don't recall elevator in my question. I didn't ask about an elevator.
I'm telling you, that's the way to understand it. The best way I know that you can understand it.
I didn't use the word elevator in my question.
What was the question?
Okay, I'll try it again. How does a vacuum create a zero gravity
It doesn't.
experience?
It
Well,
doesn't.
okay,
the vacuum just
beautiful.
removes the air, so there's no air resistance.
Yeah, Scalpel, they're missing the news. That's
No. But listen, this is the article that Rumpus gave me. It specifically says that it's a 1,000-meter tall vacuum chamber that lets scientists test zero gravity.
Right. They test those
on
phenomenon and then they try to apply it to what their hypothetical zero gravity would be.
Yeah, I know, but I'm trying to let them answer the question, not you.
Oh, I'm sorry.
It's all good, but I just want to hear what they have to say.
We said it many times before, Scalpel. They
You want to
remove
go
the
back
air.
to
So I'm talking. They remove the air, so there's no air resistance. So when things fall, they continue to accelerate without having any forces working against them. No buoyancy, no drag. Does that make sense?
Once again, how does that create a zero gravity
When you have
experience?
God.
It's clickbait.
Zanuck said it doesn't. Zanuck already answered Scalpel and said it doesn't.
No, I said the vacuum doesn't. The dropping does.
That's not what he said. See, you guys aren't.
Oh,
listening
Zanuck,
carefully.
you're saying the dropping it does, are you?
Yeah, that's what I'm saying. Let
Dropping-
them
Zanuck,
answer.
you are a
Oh my God.
science
you gotta
denier,
let him
Zanuck. Zanuck
answer.
is a
You
science
guys gotta
denier.
let
Press
him
John said it right here.
Dumber show.
Press
Question.
John.
Why
Vacuum
don't
only
you
for, I told you again.
Okay, let me ask the
Air resistance,
qualifier.
that's it.
Rumpus said if you could
Please.
press on a scale, it has weight. So if something's in a downward trajectory, I think it would have the ability to press on a scale.
Listen,
what
listen.
Rumpus said is weight.
Hold on.
In the elevator, no weight. As soon as that cable breaks, no flipping weight.
Let
ever.
me finish.
God,
the
Don,
rest.
you are so
Hold on.
obnoxious.
Let me finish the rest of the statement they make. They say also, it goes on to say, zero gravity experiments on Earth as an alternative to sending experiments to the International Space Station or zero gravity plane flight. So they're comparing a vacuum to a zero gravity situation.
No,
That's
God,
what
Scalpel.
the fucking
You can't be
article
this
says
stupid.
that he cited,
Correct.
dude.
Scalpel, you
Correct.
cannot be this stupid. Seriously.
That's
Could I say something?
This is what
God,
Rumpus
Dom.
posted.
You're a smart
Fuck
guy.
you
You're acting like
guys.
you're
Yes,
This
to
is what
understand
Rumpus
English.
posted.
You're acting like a fucking
Don't
4-year-old.
Scalpel.
Seriously, Scalpel,
Janik,
wake up.
Janik.
This is what Rumpus fucking posted.
Yes, that's what he posted. And
But you
what does
can't
it say?
read.
Yeah. What is
Zanuck,
matter? Can I say
Zanuck.
something? Can I say
Wait,
something?
let me after me.
Okay.
It says the tower is used, the vacuum chamber is used to test zero gravity. Doesn't say the tower creates zero gravity. It says it's used to.
Listen.
First, they remove the air to prevent drag. Second, they drop something from the top. And while it's falling, it's in zero gravity. How to understand?
Listen,
don't laugh.
It's
Don't
not
laugh.
zero gravity.
It's the exact same thing as the ISS.
This is,
You're both
let me
falling.
read it word
Listen,
for
guys.
word. Let me read it word for
You're
word
both
what it says.
falling. They're
Let
both
me
falling.
read it
ISS and the
word
object
for word.
are both falling in a vacuum.
Yes.
Zero G. And
I'll
let
back
me
Zanuck on that.
Let me read it word for word what it says.
Oh my fucking god!
No, please don't.
Why are you making my head
Listen.
explode?
Let him, let him, let him, let him.
A vacuum chamber.
Why
to
are you making
ISS
my head explode, Scalpel?
or a fucking
You cannot be this
parabolic
stupid.
plate.
Seriously.
Let him read, please.
Okay. I'll go
Read.
here. It says it's a 100-meter tall vacuum chamber that lets scientists test zero gravity experiments on Earth as an alternative to sending experiments to the International Space Station or zero gravity plane flight. So it's comparing this, like I said, it's comparing this fucking
They're
vacuum
identical.
chamber.
They're identical. They're identical. Both the ISS
Zanuck,
and
they
the
are not identical.
Why can't you fucking
One is in orbital free fall.
No,
The other
what
one
is
is in center of the
orbital?
Earth fall. They are
One's
not
parabolic
identical.
flight,
When
one's
you call
orbital free
bullshit,
fall.
I'm going to step in when you say
Oh
some
no,
bullshit.
you're bullshit. That's bullshit. You're
They're
calling
not identical. One is going
They're
towards the center of
identical.
the Earth, and
They're
one is going
identical.
around it.
They
There's
are
three different,
identical.
completely different situations.
No, they are identical.
I understand you're saying it's the same force acting upon it, Zanuck, but it's not apples to apples.
How,
But
how,
actually,
tell me,
Zanuck, it's not.
Don.
Hang on.
Don, how
Can I
you
say
make an
something?
experiment that will prove it?
Actually, they're not the same because the ISS is moving in a circular path, and something in the vacuum chamber is falling straight down.
Right, and the
Unless you're saying
parabolic
it's a
flight
straight
is up
path.
and down.
Unless
Nice story.
Right, so you can't say
Do
it's the
an
same thing.
experiment that will prove you are right.
And
what experiment will?
I don't have to. Is the Earth round?
Yes,
Hold
you
on. Is
make
the
it
Earth
fit.
round? I'm asking you. Is the Earth
I'm
round?
asking you for experiment that will tell us if we fall in the tower or in the ISS, so we know where.
All I said is it's not the same because the ISS, according to the heliocentric model, is moving in a circular path. And in the elevator tower, it's moving straight down. It's two different things. One's inertial, one's not inertial.
Both inertial.
Both are inertial. Something moving in a straight line at a constant velocity is inertial, but the ISS moving in a circular path is inertial too, even though it's moving in a circular path?
Yeah.
Okay, then Zanuck, is he right?
It's inertial. Make an experiment that show it's not inertial.
I thought something moving in centrifugal force is a non-inertial reference frame. Something moving in a straight path is inertial.
Does not have centrifugal force.
The ISS moving in a circular path around the Earth is you're saying it's an inertial reference frame. There's no centrifugal force involved. Real.
Paul is accelerating. Anything in a non-inertial reference frame is accelerating or turning. They're the same.
Is the ISS turning? Is the ISS turning around the Earth?
Yes.
Then it's a non-inertial reference frame.
And if you drop something, it accelerates. If it's accelerating, is it accelerating?
Well, then how can you have zero
If it's
G
accelerating,
if
it's not
if it's
inertial.
an inertial reference?
Okay,
so then your experiment.
Accelerating, it's not inertial. Is it accelerating?
Well, you tell me.
Yes, of course it's accelerating.
Okay.
If it's accelerating, it's non-inertial. If it's accelerating,
Yes,
okay. So if it, hold on, okay, let me get with you. So if hold on, so the Earth isn't accelerating, but it's also a non-inertial.
What do you mean the Earth is not accelerating? What do you mean?
It's not. It's at a stable speed. It's not accelerating.
No. What are you talking about? If it's turning, it's accelerating.
Is it?
Well, wait a minute,
yes, if you're an object on the surface, if you're a point mass on the surface of the Earth, you are accelerating.
No.
Even if your velocity, even if the magnitude, even if the velocity of the magnitude of the velocity does not change, if you change direction, you are accelerating. That's by definition acceleration. That's why they call that non-inertial. So non-inertial
wait
if you're turning,
a minute.
and non-inertial if you're accelerating. Both
The Earth is
are non-inertial.
accelerating around the
Hold on.
The
sun.
Earth is not accelerating, though.
God, are you not listening? I'll say it again, third time. If you're a point mass on the surface of the Earth or in space going around it, you are turning. If you're turning, you are accelerating. That's a non-inertial state.
Well, the Earth is accelerating around the sun then as well.
Wait a minute. This
Yes.
definition is fucking me up.
Yes.
If you're traveling in a circle, you're accelerating even
Yes.
if you're not going faster?
Yes.
So if I'm in a car going in a circle because I'm turning, even if I'm going a steady 60 miles an hour,
I love you, man.
I'm accelerating?
You're so naive. It's fun to play with you. Yes, John.
I am, but
Even in a
look, I'm
circle,
being
you're
naive,
accelerating.
okay?
Yes,
I'm being
you're
sincere, though,
accelerating.
so don't fucking kill me, all right?
Yes.
I'm
Hang
being
on, let me ask the question. Sorry, I'm going to ask the question. In this elevator experiment, is there a terminal velocity, like where,
No.
where it reaches the max speed,
No.
or will it
No.
continue accelerating?
It's continually accelerating. Because it's in a vacuum. Remember I mentioned that.
Okay. Then continue.
Make
Just
sense?
clarifying.
Hopefully it does.
No,
Don,
I don't.
if you're,
I don't. I
you
don't
have to
disagree
understand
with it.
acceleration. Don, if you are in a car going straight and accelerating or taking a turn accelerating, they're the same thing. They define acceleration is either a change in velocity or a change in direction, because velocity has both a magnitude and a direction, a vector. Now learn these terms rather than fucking fighting with us all the time.
I'm not trying to fight with this.
You
is not
are.
a fight, Zanuck.
Constantly
Zanuck.
challenging people that know.
Zanuck, you gotta ease up, Zanuck. Zanuck,
Hey,
ease
man.
up.
So the thing is can you make a turn without accelerating?
No.
Zanuck,
wrong with
you don't have
Xanax,
to
whatever
relax,
you
bro.
took made you so aggressive. No one can talk to you, man. Calm down.
Yeah, it's like you're making an acceleration from your other point, but you're actually
Now you're
not.
going to try to take it apart. Now you're going to try to take it apart to try to justify.
No, I just want to
You're
understand
ignorant.
what you're saying when you're talking about these other reference frames, okay?
I
That's why I want to understand it clearly. I'm not challenging you.
Okay, look, I'll slow down here.
They made Zanuck work overtime tonight. He's
If
pissed
you, yeah,
off.
I'm on overtime. I need a break. Listen,
Maybe take another break.
if you're thanks. If you're turning, you are changing direction. Are you not?
Yes, but is it not
Hold on.
qualified as
Let
a
me finish.
different term of
Let me
acceleration?
finish, and you'll have the answer because I know where you
Okay.
need to know. Right.
All right.
So a velocity is made up of not only a magnitude, but a direction. It's called a vector. Okay. Now, if you change either one of them, you will have an acceleration.
Okay.
Even though I know intuitively you're
So
saying, "Hey, I'm almost done. I'm almost done." I know intuitively, Don, you're thinking, "Hey, I'm not really accelerating though. I'm not going. My
Right.
speedometer still says 50 miles an hour. I'm
Right.
going on this 300-foot radius turn. How can I be accelerating if I'm not accelerating on my speedometer? Because you're changing direction. You go, oh, wait a minute. I'm being pressed to the outside of my door there. Oh, that force. That's the acceleration they're talking about. I get it. Centrifugal.
Yeah, I get that, but I guess I'm just want to clarify for reference frame terms. Even though it's quote accelerating, it still has a stable amount of energy, kind of going on. Acceleration doesn't have to do with that, right?
There's no change. There's no change in kinetic energy.
Okay, cool. Thank you. That's where I was disconnected.
And that's easy to confuse as well, because you're saying, well, if you're accelerating, why isn't your kinetic energy increasing? The centrifugal force, you have a force, but it's a balanced force, centripetal and centrifugal.
It's a change in velocity, right? Not a change in speed. It's
Right,
not,
right. It's a change in velocity.
It's
Yes.
a change in like a vector change, not
Yes.
a change in speed. That's
Correct.
totally different, though, Zanuck. You need to be clear.
No,
it almost
I
seems
said
like
that very
you're.
clear. I said that very clearly. I said velocity.
No, but acceleration is a change in speed.
No, it's a change in direction as well as a change in speed. You
Yeah,
said
but that has
vector.
to do with velocity and
You
vector.
had it right the first time. Now you're going wrong. Listen, the acceleration is a change in velocity. Velocity has two components. It has a magnitude and it has a vector. Okay? So if you change any one of those two, you're having acceleration.
Yeah, but you're equating it to speed. You need to be careful.
I'm not equating it to speed.
I knew the answer, and I thought you were talking about. Well, that's what you made it seem like.
No, I'm not trying to like anything other than it is. You change
You knew
direction.
Don was thinking about speed, right? You
Yeah,
knew
it would
Don
have
was.
centripetal acceleration. The centripetal acceleration will hold it in
So
place.
you could have said that. You could have said velocity and vector change.
Velocity has a direction and a magnitude.
Okay, well now we can continue, but it's a little.
Look,
that's what I keep
trying to be
telling
as
you. It's a
detailed
little.
and as patient.
No, but you're not being detailed. When I told you, you could have used vector and all that to be more detailed, and
I
people would
did.
have
I said
understood
that
better.
specifically. I said that.
All right.
I said velocity is made up of a vector, direction, and its magnitude. Think of magnitude as the speed.
I got you. Y'all was just man, and which reference frame is called what, and this and this and that.
Don't even go to reference frames. You don't need to go to reference frames. You can if you want.
Y'all, that's where y'all were on. That's where I jumped in. I just wanted to make sure I knew what you're saying. It's like even though one's moving, it's the non-inertial because it's stable.
Listen, if you're in a non-inertial reference frame, that reference frame is accelerating, which means rotating or accelerating. Either you're rotating,
but then the other one is also accelerating, right?
What other one?
Like let's just use the Earth and the plane for example. Aren't both objects?
No. Oh yeah, because they're going around a circle. Yeah, they're both non-inertial.
Right. So it's hard to feel like, hey, if I'm like, what's the rule of the non-inertial reference frame? Oh, the rule is it's accelerating.
No,
I thought the other one was.
Hold on. You got to remember it's where motion is being viewed from. Where you view that motion from. From what environment are you viewing that motion? The entire environment, not
from
just
the non-inertial.
Not just the object. The entire environment viewed from the entire environment. Any reference point can be in that environment, can it not? So the environment is rotating, the environment is accelerating, the environment is not rotating or accelerating. That's what you have to clarify. Which environment you're looking at the object from.
Right. So the one we're on that is rotating and accelerating.
Now you're making
Sorry, Zanuck. I mean, sorry I said we're on the Earth, okay? When we're in the Earth. Excuse me.
No, not even in
anyway.
We're in the inertial.
Dude, I'm joking.
In the reference frame.
Come on. I mean, you know what I mean? That's serious.
No, I can only tell what the words you use. I'm not a mind reader.
Seriously, man. Come on, man.
Trying to help you, bro.
So we're in.
Zanuck, you know what context is. You know what he means.
No, because you start thinking that, he said, because he's going, I know where he's going. Why is the plane left off the ground and why isn't the Earth rotating underneath it?
No, Zanuck, I just want to clarify what the words are. Like, so we're on the non-inertial reference in the non-inertial reference frame, and it's accelerating.
Yes.
And the other object is the inertial reference frame?
The other object can be accelerating too. It's another reference frame, or it's in your reference frame.
So that's also a non-inertial.
Yeah.
Or it's inertial because we're viewing it? If we're viewing it, it becomes
think about it this way. Here's the rule of thumb.
I just want to know the words,
If any force,
I can see this shit happening.
Listen, if any force is acting on it, it is non-inertial. Doesn't mean it's
everything. So everything's non-inertial then.
If there's a force acting on it, yes. But everything isn't, because there are some things that are not acting on it.
No, because there would have been force from the Big Bang origin of time, that all that momentum's been conserved forever, even if you appear in space fucking out of nowhere. I mean, you literally are never going to have anything that isn't moving, ever.
Well, to your point, you think that everything should be slowing down because, right, it's going from the point of singularity and a rapid expansion. Why is everything accelerating without a force? That contradicts the laws of the conservation laws. That's why they come up with dark energy and dark matter.
Yeah, of course.
That's where the Newtonian laws.
They came up with it because gravity's busted. That's why.
Right. Yeah. I mean, he just doesn't want to say it that way.
Hey, Hank, have you heard of dark water? Dark water?
Damn it! Like the Pirates of Dark Water?
Yeah. When your
monkey
toilet
birds.
backs up. Yeah, when your toilet backs
monkey
up.
birds.
No, it's a new theory. They're trying to take the place of dark energy and dark matter to replace those two. They came up with dark water. I swear I've heard it. I'm not making this up. I don't know.
I've heard of dark gravity.
Maybe that's...
You understand that when people are saying dark, whatever, is that they really don't quite understand yet.
Yeah, that's the name that they're giving it. I understand, but it's a theory that's replacing dark matter and dark energy.
It's a hypothesis.
Dark heart.
It's not replacing it. It's a competing theory, I think. Is
It's a hypothesis.
Yeah, competing. So you've heard of it?
Competing.
I've heard you talk about it, sir.
Yeah, that's why I'm trying to find out where I saw it or heard it.